For all of human history, we've looked up at the night sky and seen a random scattering of stars. We've painted a portrait of our universe as a vast, dark canvas, sprinkled with brilliant, solitary islands of light. It feels chaotic, like a cosmic lottery of where galaxies appear and where they don't. But what if that randomness is a grand illusion? What if everything in existence is connected by a hidden skeleton, a cosmic web that forms the true, mind-bending architecture of our universe? Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This isn't science fiction. It's the frontier of modern cosmology. Beneath the apparent chaos lies an ordered, intricate, and impossibly large structure. It's a network of shimmering filaments, dense knots, and terrifyingly empty voids that dictates where galaxies are born, how they live, and where they die. Today, we're not just going to look at this web. We're going on a journey to understand its true scale, to travel from the threads it's woven from to the incomprehensible emptiness that separates them. We'll explore how it was built, who its invisible architect is, and how shocking new discoveries are forcing us to rethink everything we thought we knew about the universe's largest structures. It's time to have your sense of scale completely redefined. Imagine for a moment that our entire galaxy, the Milky Way, with its hundreds of billions of stars, is just a single speck of dust. Now, picture that speck of dust caught in a single thread of a spider's web. But this web isn't in your garden, it stretches for billions of light years in every direction. The threads are highways of gas and dark matter, and where they intersect, you don't find a fly, you find a supercluster of 1,000 galaxies, all buzzing with activity. This is the cosmic web. It's the universe's hidden skeleton, and we're living inside it. The question isn't just what it is, but how big is it, really? The answer will take us to the very edge of imagination and to the largest things humanity has ever seen. The Great Revelation. From chaos to structure. For much of the 20th century, our picture of the universe on the grandest scale was, frankly, a bit blurry. After Edwin Hubble confirmed that those faint smudges in the sky were other galaxies' entire universes beyond our own, the prevailing idea was one of uniformity. It was thought that if you zoomed out far enough, galaxies would be distributed more or less evenly, like a fine mist. It was a tidy, if not very exciting, picture. That comfortable idea was shattered in 1989. Astronomers Margaret Geller and John Huchra were painstakingly creating a three-dimensional map of the universe. They weren't just taking pictures, they were measuring the redshift of each galaxy to calculate its distance, plotting its true position in space. As they mapped a slice of the cosmos, a shocking pattern began to emerge. The galaxies weren't spread out like a uniform gas at all. Instead, they were arranged in a stunning, lace-like pattern. They had discovered what became known as the Great Wall, a colossal sheet of galaxies stretching over 500 million light-years long and 200 million light-years wide, but only about 15 million light-years thick. It was like finding a mountain range on a planet you thought was perfectly smooth. For so long, this structure had been hiding in plain sight, its existence only becoming clear when you added that third dimension of depth. This discovery was the first major clue. The universe wasn't a random jumble, it had architecture. As more surveys, like the Sloan Digital Sky Survey, mapped the sky with ever greater precision, the picture became clearer. The universe looks something like a sponge. It's a vast, interconnected network. Cosmologists call it the cosmic web. So what are the pieces of this grand design? The structure basically breaks down into three parts. First, you have the asterisk filaments. These are the web's most defining feature, enormous, thread-like structures of galaxies, gas, and dark matter stretching for hundreds of millions of light years. Think of them as the great cosmic highways, channeling matter and energy across the universe. These aren't flimsy threads, they're packed with the mass of billions of galaxies. Next are the asterisk nodes, or clusters. These are the bustling intersections where the filaments meet. At these cosmic crossroads, the density of matter is at its highest. Here, gravity has pulled in so much material that thousands of galaxies are crammed into dense, gravitationally bound superclusters. These are the great cities of the universe, blazing with the light of trillions of stars and superheated gas. And finally, you have the asterisk voids. These are maybe the most mind-bending feature of all. Between the glowing filaments and nodes lie vast, dark, and almost entirely empty regions. And these aren't just small gaps, they are colossal, nearly spherical bubbles of nothingness that can span hundreds of millions of light years. They are the great cosmic deserts, so empty they make the space between galaxies seem crowded. It's within these components, filaments, nodes, and voids that the true, staggering scale of the universe begins to show itself. The invisible architect, the mystery of dark matter. To understand how this colossal web got built, we have to talk about something we can't see, touch, or detect directly. We have to talk about its invisible architect, dark matter. The story of the cosmic web is really the story of dark matter. All the glowing galaxies, hot gas, and brilliant stars we can see make up only about 5% of everything in the universe. Around 27% is dark matter, and the rest is the even more mysterious dark energy. That means for every bit of matter you can see, there are more than 5 bits of this invisible stuff hiding in the shadows. We know dark matter exists not because we see it, but because we see what it does. We see its gravity bending the light from distant galaxies, a phenomenon called gravitational lensing. We see its influence in the way galaxies spin. Without a huge halo of invisible matter surrounding them, their outer stars should be flung off into space, but they aren't. Dark matter provides the extra gravitational glue that holds galaxies together. It's the puppet master, and the visible universe is the puppet. So how did this invisible substance build the biggest thing in existence? The answer goes back to the first moments after the Big Bang. The early universe was an incredibly hot, dense, and remarkably uniform soup. But it wasn't perfectly uniform. There were tiny, quantum-level fluctuations in density, minuscule regions that were infinitesimally denser than others. These primordial ripples, which we can still see imprinted on the cosmic microwave background, were the seeds of everything. As the universe expanded and cooled, gravity started to take over. Normal matter, the stuff that makes up you, me, and the stars, was still caught in a hot, high-pressure plasma, pushing back against gravity's pull. But dark matter was different. It doesn't interact with light or electromagnetism, so it felt no pressure. It was cold, meaning it wasn't moving around much, and it was free to respond to one force and one force only: gravity. Those tiny, denser regions from the early universe began to attract more and more dark matter, starting a gravitational runaway effect. Areas with slightly more dark matter pulled in even more, creating what are known as dark matter halos, vast, spherical clouds of this invisible substance. These halos were the first structures to form, the gravitational wells, the scaffolding upon which everything else would be built. Over hundreds of millions of years, these halos grew and merged. Computer simulations that model this process are breathtaking. If you plug in the initial conditions of the universe, add dark matter and gravity, and let the simulation run for billions of years, a familiar pattern always emerges: a beautiful, complex, interconnected web. The dark matter formed the structure first. It collapsed into vast sheets, which then broke apart into long filaments. The normal matter, the gas, was then drawn by gravity into this pre-existing dark matter framework, like iron filings aligning to a hidden magnetic field. This gas flowed along the dark matter filaments, condensing and cooling in the deepest gravitational wells, the halos, where it finally ignited to form the first stars and galaxies. So when you see a map of the cosmic web, you're not just looking at a pattern of galaxies. You are looking at a luminous blueprint of an invisible dark matter skeleton. The filaments are rich veins of dark matter, and the galaxies within them are like dewdrops clinging to a spider's web, formed only where the web was already spun. Understanding this is key. The cosmic web isn't a web of galaxies, it's a web for galaxies, built by an invisible architect using gravity as its only tool. The zoom out. A journey of unimaginable scale. Now we get to the heart of our question. How big is the cosmic web, really? To truly get a feel for the scale, we can't just throw out numbers. We need to take a journey. Let's start from our own cosmic backyard and zoom out, step by step, until our minds can barely contain the sheer immensity of it all. Step 1. Our place in the emptiness. Our journey begins with a startling revelation. We kind of live in a hole. Our Milky Way galaxy and our entire local group of galaxies are located inside a vast cosmic underdensity. It's called the KBC void, named after the astronomers Keenan, Barger, and Cowie who identified it. This isn't a perfectly empty void, but a region of space significantly less dense than the cosmic average. But its scale is the first shock to our system. The KBC void is estimated to be roughly 2 billion light-years in diameter. A beam of light would take 2 billion years to cross it, and our galaxy is located within a few 100 million light-years of its center. We aren't in one of the universe's bustling cities, but out in the cosmic suburbs, one of the quietest regions of the known cosmos. Step 2. The cosmic highways. The filaments. As we zoom out from our local void, we begin to see the glowing boundaries that define it, the filaments. These are the long, winding bridges connecting the great islands of galactic density. A single filament can stretch for unimaginable distances. Some have been measured to be over 50 million light-years long. That's 20 times the distance between our Milky Way and our nearest large galactic neighbor, Andromeda. But what are these filaments actually made of? A tiny fraction is the visible light from galaxies. The vast majority, of course, is the dark matter scaffolding. But there's a third crucial ingredient: gas. Most of the universe's normal matter isn't locked up in stars. An estimated 40 to 50% of it exists as a hot, incredibly diffuse plasma that permeates the filaments, known as the warm hot intergalactic medium, or WIM. This gas is mind-bogglingly tenuous, with a density of only about 10 to 100 particles per cubic meter of vacuum, far emptier than anything we can create on Earth. Yet, because the filaments are so incomprehensibly vast, this sparse gas adds up to be about half of all the visible matter in the universe. It's heated to temperatures between 100,000 and 10 million Kelvin, glowing faintly in X-rays, which is how astronomers have finally detected it. This WIM is the fuel for galaxies, flowing along the dark matter filaments and providing the raw material for star formation. And some of these filaments are simply monstrous. After the Great Wall, others were found, like the Pisces-Cetus supercluster complex, a filament system about 1 billion light-years across. But even that is dwarfed by the current contender for the record. Discovered by mapping distant, powerful explosions called gamma-ray bursts, the Hercules Corona Borealis Great Wall is, for now, the largest known structure in the universe. It's a colossal arrangement of galaxy clusters and matter that is estimated to be a staggering 10 billion light-years long. That is almost 10% of the diameter of the entire observable universe. However, its existence is highly debated. A structure this large is so extreme that it challenges the cosmological principle, the idea that the universe should be basically the same everywhere on the largest scales. Many astronomers question if it's a real, single object or a statistical illusion in the data. Step 3. The cosmic cities. The nodes. Where these immense filaments cross, we find the nodes. If filaments are the highways, nodes are the sprawling, chaotic, super-dense metropolitan areas of the universe. These are the galaxy clusters and superclusters, the most massive gravitationally bound objects we know of. A single rich cluster, like the nearby Coma cluster, can contain over 1,000 galaxies, all swirling around a common center of gravity in a region only a few million light-years across. The space between the galaxies isn't empty either. It's filled with an even hotter gas, the intracluster medium, heated to tens of millions of degrees by the cluster's immense gravity. The power of these nodes is so great they act as giant cosmic lenses, warping spacetime itself and magnifying the light from even more distant galaxies behind them. Step 4. The Great Nothing, the Voids. Finally, to appreciate the scale of the web, we have to return to the voids. While the filaments and nodes have the action, the voids have the asterisk scale. They make up roughly 80% of the volume of the universe. The largest known voids are simply called supervoids. The giant void is a desolate expanse estimated at over 1 billion light-years in diameter. Our own KBC void is even larger. To travel across one of these at the speed of light would be a journey longer than it took for multicellular life to evolve on Earth. Are they truly empty? Not completely. They are home to a few, lonely, void galaxies. These galaxies are fascinating because they evolve in extreme isolation, living quiet lives in the great cosmic wilderness, shielded from the violent collisions that shape galaxies in the web's busier neighborhoods. Step 5. Where the pattern ends. There's one final step. What happens if we keep zooming out? Past the voids, past the giant walls, past everything? Eventually, the pattern disappears. At a scale somewhere around 1 billion light-years, the universe stops looking like a web and starts looking uniform again. The filaments, nodes, and voids average out into a smooth, homogeneous distribution. There appear to be no structures larger than this scale. Cosmologists call this transition point the asterisk end of greatness. It is the scale where the magnificent, intricate design of the cosmic web fades into the background, and the universe finally becomes the same everywhere. This end defines the upper limit of the web itself. The cosmic web is the largest structured thing in the universe, but it is not the universe itself. It's a pattern that exists within a larger, ultimately uniform cosmos. A living, spinning skeleton. For a long time, we imagined the cosmic web as a static scaffolding that formed and has remained more or less the same ever since. But recent discoveries have completely upended that view, revealing that the web is not a dead skeleton, but a dynamic, evolving, and spinning entity. Starting in 2021, astronomers using both powerful computer simulations and observations of real galaxies began to uncover something extraordinary.
They found that the immense filaments of the cosmic web aren't just sitting there. They appear to be slowly rotating. We're talking about structures hundreds of millions of light-years long, spinning like giant corkscrews in space. Until then, galaxy clusters were the largest things known to rotate. Finding spin on an even larger scale was a genuine shock. This finding has profound implications. It suggests that the cosmic web doesn't just provide a path for galaxies, it can actively impart spin to them. The theory is that as gas flows along these rotating filaments, it gets twisted, and that angular momentum is inherited by the galaxies that form from that gas. It's like discovering that the river itself is twisting the stones that form on its bed. This challenges our models of how galaxies get their rotation. It implies a much more intimate, dynamic relationship between a galaxy and its cosmic environment. The web itself acts like a cosmic torque wrench, twisting galaxies into motion as they form. This is just the beginning of a whole new chapter in cosmology. Upcoming observatories like the Vera C. Rubin Observatory and the Euclid Space Telescope are designed specifically to map the web with unparalleled precision. Euclid will create a 3D map of the universe by observing billions of galaxies up to 10 billion light-years away. These missions will search for more of these spinning filaments, to test whether this is a rare fluke or a fundamental property of the cosmos. They will give us a high-definition view of this hidden architecture, potentially revealing the deepest secrets of its construction. The cosmic web is one of the most profound discoveries in science. It transforms our view of the universe from a collection of isolated objects into a single, interconnected entity. Every galaxy, every star, every planet including our own is part of this one, gargantuan structure. And we are just starting to understand it. New telescopes are peering deeper, and every observation brings new questions and new wonders. If this journey into the mind-bending scale of our universe fascinated you, make sure to subscribe and hit the notification bell. We post new videos every week exploring the biggest questions in cosmology. And we'd love to know what you think. What part of the cosmic web blows your mind the most? Is it the disputed size of the Hercules Corona Borealis Great Wall, the profound emptiness of the voids, or the new discovery that the web itself is spinning? Let us know in the comments below. From the chance discovery of the Great Wall to the intricate maps of today, our perception of the universe has been fundamentally altered. The random spray of galaxies we once imagined has been replaced by the breathtaking reality of the cosmic web. We have journeyed from our quiet home in the KBC void, across filamentary highways paved with dark matter and glowing with hot gas, to the bustling galactic cities at the nodes. We have stared into the abyss of the great voids and traveled to the very end of greatness, where structure gives way to uniformity. We've learned that this web is not just a relic of the past, but a dynamic, spinning entity that continues to shape the evolution of every galaxy within it. It is the hidden skeleton of existence, the invisible architecture that dictates the grand pattern of the cosmos. The next time you look up at the night sky, remember that you aren't just seeing a random collection of stars. You are looking through the walls of our local void, out at the distant, glittering threads of a single, magnificent, and incomprehensibly vast cosmic web. You are looking at the true shape of the universe. And we are just beginning to explore it. Part 2, the first map of the universe. If the night sky feels random when you look at it with your eyes alone, that is because your eyes are only seeing a thin surface, a flat impression, a kind of glowing wallpaper spread across the dark. Stars seem sprinkled across the sky without any obvious plan, and the faint galaxies beyond them seem even more scattered, like distant dust caught in black water. For a very long time, that was enough to shape our imagination. The universe looked busy, beautiful, and more or less chaotic. But there is a quiet difference between looking at something and mapping it. Looking tells you that something is there. Mapping tells you where it truly lives. And that difference changed everything. If these slow journeys through science help you relax at night, you can gently support the channel with a like or a quiet subscription. And if you ever feel like it, you can leave a comment about where in the world you're listening from. It is always a peaceful reminder that even on a tiny planet, under one small sky, curiosity travels very far. To understand how the cosmic web was discovered, we have to go back to a time when astronomers were still trying to answer a very basic question. Not what the universe means, or how it will end, but something much simpler. Where, exactly, are the galaxies? That may sound like an easy thing to ask. After all, if a galaxy is visible in a telescope, surely it can just be placed on a map. But the sky creates an illusion. When you look upward, everything appears pressed onto the inside of a giant sphere. A nearby bright star and a galaxy that lies hundreds of millions of light years beyond it can seem like neighbors, simply because they appear close together from our point of view. The sky hides depth, and depth is the whole secret. Imagine standing on a hill at night and seeing the lights of a distant city. From far away, the lights might look like a flat sheet, a glittering pattern on the horizon. But if you were able to fly over that city, you would see streets, neighborhoods, towers, bridges, parks, and empty spaces in between. What seemed like a flat glow would suddenly reveal structure. The universe was waiting for that same kind of revelation. It was waiting for humanity to stop looking at the sky as a flat image and begin measuring it as a true landscape. In the early 20th century, astronomy was already changing quickly. Telescopes were becoming more powerful. Observatories were gathering better photographs. And one of the most important discoveries in scientific history had already begun to reshape our place in the cosmos. Those faint, cloudy smudges once called spiral nebulae were not small objects inside the Milky Way. They were separate galaxies. Entire island universes of stars, each one vast beyond ordinary imagination. That alone was a staggering shift. The universe became much bigger almost overnight. But once astronomers understood that galaxies were real systems far beyond our own, a new problem appeared. If there were millions, then billions, of galaxies out there, how were they arranged? Were they spread smoothly in all directions? Did they gather into groups? Were there giant patterns hidden beyond the reach of the naked eye? Or was everything, on the largest scales, basically uniform and featureless? For a while, the safest assumption was that if you zoomed out far enough, matter would look evenly distributed. Not perfectly smooth, of course. There would still be clusters and local gatherings. But on the grand scale, many scientists expected the universe to become plain, homogeneous, more like a mist than a city. It was a reasonable idea. And for a time, it was very hard to challenge, because the maps simply did not exist. A proper cosmic map needs more than direction. It needs distance. This is where one of the most elegant tools in astronomy entered the story. Light does not arrive empty. It carries information. And when astronomers spread that light out into a spectrum, much like a rainbow, they can read it like a code. Hidden inside are lines that reveal what an object is made of, how hot it is, and, crucially, whether it is moving toward us or away from us. As the universe expands, distant galaxies are generally carried away from us, and their light becomes stretched. That stretching shifts the light toward the red end of the spectrum. Astronomers call this redshift. The greater the redshift, the farther away a galaxy usually is. It is such a quiet, beautiful idea. A galaxy speaks through light, and by listening carefully, we learn not only what it is, but how deep into the universe it rests. This transformed astronomy from a two-dimensional art into a three-dimensional science. Once redshift measurements became more common, astronomers could begin doing something that earlier generations could only dream of. They could assign galaxies positions not only across the sky, but into the depth of space. A point was no longer just left or right, north or south. It could now also be near or unimaginably far. But collecting that information was slow work. Very slow work. Today we live in an age of giant automated surveys, powerful computers, and instruments that can collect enormous amounts of data in a single night. But the first great maps of the universe were built with patience. Every galaxy had to be observed. Its light had to be captured. Its spectrum had to be measured. Its redshift had to be calculated. Then its position had to be plotted. It was not glamorous work in the way people sometimes imagine science. It was methodical, repetitive, quiet, a little like counting grains of sand on a beach, except every grain was a galaxy the size of the Milky Way. And yet this kind of work is often where the deepest surprises hide. One of the key moments in this story came with surveys that tried to chart not just a few galaxies, but tens of thousands of them. Astronomers began taking slices of the universe, narrow regions of sky studied in detail, and plotting galaxies by both angle and distance. These diagrams started to look less like star charts and more like cross-sections through space itself. At first, the results were subtle. Small clusters appeared. Some regions seemed denser than others. Galaxies were clearly not scattered with perfect smoothness. They gathered in families. They seemed social, gravitationally attracted. There were groups, clusters, and maybe larger associations beyond them. But the real shock came when the data became rich enough to reveal something bigger than local clustering. In the late 1970s and especially into the 1980s, astronomers began seeing hints that the universe might not be filled evenly at all. Instead of a gentle fog of galaxies, there were boundaries, gaps, long stretches where many galaxies seemed to line up, and nearby there were strangely empty regions where very few appeared. It was as if the universe were beginning to confess that it had bones. Among the most famous early efforts was the Center for Astrophysics Redshift Survey, often remembered through the work of astronomers like Margaret Geller and John Huchra. They were mapping galaxy positions in a way that allowed large-scale patterns to emerge with startling clarity. When the results were displayed, they did not resemble a uniform cloud. They looked textured, layered, structured. Then came one of those moments science sometimes gives us, when a quiet expectation suddenly breaks apart. The galaxies formed what looked like a huge wall. Not a wall in the sense of something solid, of course, but a giant sheet-like arrangement of galaxies stretching across an enormous region of space. Later named the Great Wall, it extended for hundreds of millions of light years. For people used to thinking in terms of galaxy clusters and modest groupings, this was astonishing. It suggested the universe contained structures far larger than many had expected. The emotional impact of a discovery like that is hard to overstate. It was not just that a large object had been found. It was that the universe was revealing style, architecture, a preference for patterns on scales that pushed against human intuition. And once you see a pattern, you begin to search for it everywhere. More surveys followed. Better instruments arrived. Larger catalogs grew. The story kept repeating. Galaxies did not simply float alone. They traced arcs, chains, filaments, and sheets. Clusters appeared where these features intersected. Between them lay regions so underpopulated they seemed almost hollow. If you could drift far outside the Milky Way and look back at the universe on the largest scales, you would not see a smooth soup of galaxies. You would see something closer to a network. Not neat like graph paper. Not symmetric like a snowflake. But undeniably connected. A web. That idea did not appear all at once in a single dramatic second. It emerged gradually as map after map deepened the same truth. The universe had texture. One reason this discovery was so powerful is that it changed a philosophical feeling as much as a scientific one. A random universe feels different from a structured universe. In a random cosmos, galaxies are lonely islands. In a structured cosmos, galaxies belong to a wider geography. They are not merely scattered. They are placed within an evolving pattern shaped by deep physical rules. And perhaps this is one reason the discovery feels so compelling even to people who are not astronomers. Human minds are drawn to hidden order. We feel it in coastlines, routes, lightning, river deltas, and winter branches. Nature often builds not with rigid symmetry, but with repeating pathways and tangled networks. When the universe turned out to have its own version of that pattern, it felt strangely familiar. Vast and alien, yes, but also recognizable, as though the same love of structure had been written into matter from the beginning. There is another reason the first maps were so important. They taught astronomers humility. Before the data, many ideas about cosmic structure were guided by theory, intuition, and limited observation. But the maps forced everyone to look directly at what the universe had actually done. And the universe, as it often does, turned out to be more imaginative than the neatest human guesses. A map can do that. It can correct pride. Think of ancient explorers standing before coastlines no one in their world had ever charted. At first they might imagine the land continues smoothly, gently, perhaps predictably. Then the real shoreline appears, full of bays, inlets, cliffs, hidden coves, and strange bends. The world is more detailed than the mind expected. The first three-dimensional maps of galaxies had the same effect. The shoreline of the cosmos was not smooth. It had continents of light and oceans of near nothing. Some of the most haunting features on those maps were not the dense regions, but the empty ones, the voids. When astronomers began plotting galaxies in depth, these empty regions stood out almost as strongly as the crowded ones. It was one thing to find giant structures. It was another to discover that much of the universe seemed made of absence. That contrast gave the maps their strange beauty. Bright groupings and dark gaps, threads and hollows, density and silence. And for a sleep-focused story like ours, there is something almost dreamlike about that image. The universe is not just full. It is also spacious in a way that defies comfort. It breathes through emptiness. Galaxies gather along vast boundaries, while inside the cosmic bubbles between them there can be almost nothing at all. Not nothing in the absolute sense, but so little that our ordinary intuitions about space begin to fail. By the late 20th century, the idea of large-scale cosmic structure was no longer a suspicion. It was becoming the new picture of the universe. Then came even more ambitious projects, like the Sloan Digital Sky Survey, which would map the positions of galaxies on a scale earlier astronomers could barely have imagined. These surveys did not erase the older discoveries. They confirmed and expanded them. They turned the first hints of structure into an overwhelming case. With enough data, the cosmic web stopped looking like a metaphor and started looking like a measured fact. This is one of the quiet revolutions of modern science. There was no single explosion of revelation visible to ordinary life. No sudden change in the sky above our houses. No planet shifting course. But inside observatories and data archives, humanity's idea of the universe changed shape. We moved from seeing galaxies as a scattered to seeing them as a system. And systems invite deeper questions. If galaxies line up in filaments, what placed them there? If enormous walls exist, how did they form? If voids are so large, why are they so empty? And why should the universe prefer this kind of pattern instead of another? The first map did not answer those questions. It gave us something even more valuable. It proved they were the right questions to ask. This is often how science progresses at its most beautiful. First comes the instrument, then the measurement, then the surprise, then a longer silence, where new theories must be built to match what reality has revealed. In this case, the surprise was enormous. The architecture of the cosmos was far more dramatic than expected. The universe had neighborhoods, corridors, crowded intersections, and deserts so large they barely seemed possible. It was not a flat field of lights. It was a terrain. And yet, from inside one galaxy, deep within one quiet corner, all of that structure is hidden unless we deliberately uncover it. That is one of the most lovely things about the story. The cosmic web was not hidden because it was small or faint. It was hidden because it was too large to see without perspective. Some truths are invisible not because they are subtle, but because they are immense. That idea has a kind of tenderness to it. We often imagine knowledge as a matter of looking harder, closer, with more focus. But sometimes understanding comes from stepping back far enough to let the pattern appear. The first map of the universe was not simply a catalogue of galaxies. It was humanity learning to step back. And once we stepped back, the universe no longer looked random. It looked connected. If you pause here for a moment and imagine those early astronomers, night after night, measuring the faint light of distant galaxies, there is something deeply peaceful in it. They did not know, at first, what the final picture would be. They were simply patient enough to let the universe reveal itself piece by piece. A spectrum here, a redshift there, another plotted point, another faint clue. And then, slowly, the larger image emerged. A wall, a filament, a void, a pattern, a web. If you have ever felt that science can sometimes seem cold or mechanical, this part of the story offers a gentler view. Discovery is often not a sudden conquest. It is a conversation with nature carried out in whispers, a long act of attention. The universe does not shout its structure at us. It lets us notice it, and once noticed, it becomes impossible to unsee. The stars overhead still look scattered to the naked eye. The night sky still feels serene and almost random when viewed from Earth. But behind that familiar appearance is a depth-filled reality, a hidden geography traced by light and gravity over billions of years. The first maps gave us entry into that geography. They were the beginning of a new way of seeing. In the next stage of this journey, those maps become even more vivid, because we begin to ask not just whether structure exists, but what that structure actually looks like. What is a filament, really? What lives inside it? What makes a node different from a void? And how can something so large still have a shape delicate enough to be called a web? Before we get there, though, it is worth resting with the discovery itself. For most of human history, the universe was a ceiling. Then it became an ocean. Then, with the first real maps, it became a landscape. And landscapes have form. They have pathways. They have empty valleys and crowded ridges. They guide what flows through them. They create relationships between places. The cosmic web begins with that realization. The universe is not only full of galaxies, it is arranged. That may be one of the most comforting scientific facts of all. Because in a cosmos so large it threatens to erase every familiar scale, there is still pattern, still structure, still a hidden order waiting to be noticed. And perhaps that is why the first maps remain so moving. They did more than locate galaxies. They gave shape to the unknown. If this quiet corner of science has helped your mind slow down a little tonight, you can leave a small like, or subscribe for more calm journeys through physics and space. And if you feel like sharing, I would love to know which image stays with you most, the Great Wall, the deep voids, or the idea of the universe slowly revealing its pattern through light. For now, let the map rest in your mind, not as a chart of numbers, but as a gentle shift in perspective. The sky above us is not a flat spray of lights. It is a deep and structured place. A place with distance, architecture, and hidden design. A place where every galaxy occupies not just a point, but a position within something larger. And that larger thing is only beginning to come into view. Part 3: The Discovery of the Cosmic Web. Once the first real maps of the universe began to appear, something quietly unsettling happened. The galaxies refused to behave like dust in empty space. They did not settle into the smooth, gentle spread many people had expected. Instead, they gathered. They stretched. They curved into long arrangements and then left behind enormous dark gaps. The more carefully astronomers mapped the cosmos, the less random it seemed. It was as if the universe had been hiding a pattern so large that no one could notice it until enough of the sky had been measured all at once. And that is where the idea of the cosmic web truly began. Not in a single flash of certainty, but in that strange moment when repeated maps started whispering the same message. The universe has structure. It has shape on scales so large that human language almost fails. Galaxies are not simply scattered through space. They trace something bigger than themselves. If these quiet science journeys help you unwind at night, you can gently support the channel with a like or a soft subscription. And if you feel like it, leave a comment telling me what time it is where you are listening. There is something calming about imagining this story moving through different corners of the world while the same universe stretches above all of us. What made the discovery of the cosmic web so powerful was that it did not come from a single photograph. You cannot point a telescope at the sky and take one neat picture of the whole web the way you might photograph a tree or a mountain. The web is too large, too faint, and too spread across depth. It had to be assembled from evidence, piece by piece, galaxy by galaxy, survey by survey. It was less like finding an object and more like realizing that a hidden design had been present all along. At first, the evidence looked a little messy. Astronomers saw galaxy clusters, then chains of clusters, then sheets and walls, then wide regions where almost nothing seemed to be present. It was tempting to treat each of these as separate curiosities. A cluster here, a void there, a wall somewhere beyond. But slowly, the pieces stopped looking separate. They began to look connected, as though all these discoveries were fragments of one larger architecture. This is often how scientific understanding deepens. At first, reality seems to offer unrelated puzzles. Then, little by little, those puzzles start fitting together. And what once looked like many small mysteries turns out to be one much bigger truth. The bigger truth here was that the universe does not merely contain galaxies. It organizes them. To appreciate how strange that idea is, it helps to step away from astronomy for a moment and think about something more familiar. Imagine standing above a dark landscape at night and seeing the lights of towns and cities below. If the lights were truly random, there would be no roads, no dense centers, no empty countryside, no rivers guiding settlement, no pattern of movement or gathering. But real landscapes do not work like that. Roads connect places. Resources shape where people build. Some regions become crowded, while others remain open and quiet. The lights on the ground reflect a deeper structure underneath. The cosmic web is something like that, except on a scale almost beyond imagination. Galaxies are not arranged according to roads or rivers, of course, but according to gravity, dark matter, and the long history of cosmic evolution. They appear where the universe made pathways. They gather where matter pooled. They avoid the great empty regions in between. As more redshift surveys were completed, astronomers began producing maps that looked almost organic. Some compared the structure to a sponge, others to soap bubbles pressed together, others to a network of filaments. The exact analogy did not matter as much as the underlying realization. The large-scale universe had texture. Dense ridges of galaxies surrounded immense empty cells. These empty cells, later called voids, were not tiny gaps. They were enormous. Some stretched across hundreds of millions of light years. The galaxies, meanwhile, traced the borders and intersections between them. That pattern is one of the great visual surprises in science. Many people, before they see a real large-scale map of galaxies, imagine the universe as full in every direction. Vast, yes, but crowded. In reality, the large-scale cosmos is also defined by emptiness. It is not only what is present that matters. It is what is absent. The web glows partly because the voids around it are so deep and so dark. There is something almost poetic in that. The structure of the universe becomes visible not just through its richness, but through its silence. By the late 20th century, this picture was growing stronger. Survey after survey revealed the same broad truth. Galaxies preferred company. They lined up in filaments and clustered at intersections. The universe looked less like a fog and more like lace, less like static and more like design. But a difficult question remained. Was this pattern only in the visible matter, or was it telling us something deeper about the entire cosmos? This question mattered because galaxies, as large and luminous as they are, represent only a small fraction of what exists. Most of the matter in the universe is dark matter, invisible to telescopes, known only through its gravity. If the visible galaxies were tracing a web, perhaps that web was only the glowing surface of a much larger invisible structure. And this is where observation and theory began to meet in a beautiful way. Physicists had already been developing models of how the early universe evolved after the Big Bang. According to these models, the young universe was not perfectly smooth. It contained tiny fluctuations in density, small unvenuses left over from its earliest moments. At first these differences were extremely slight, almost unbelievably subtle. But gravity is patient. Over immense stretches of time, even tiny differences can grow. A region with a little more matter pulls in more matter. A denser place becomes denser still. When scientists ran computer simulations using these initial conditions, something remarkable happened. The matter did not collapse into one giant lump, and it did not remain evenly spread. Instead, it formed a pattern of sheets and filaments surrounding voids. It formed, in other words, something that looked astonishingly like the maps astronomers were discovering in the real universe. That was one of the most satisfying moments in modern cosmology. The observed universe and the simulated universe began telling the same story. This did not mean every detail was settled. Science is rarely that simple. But it meant the cosmic web was becoming more than an observational curiosity. It was becoming a central feature of how the universe grows. The simulations also helped explain why the structure had that specific appearance. Matter did not collapse everywhere at the same rate. It tended to fall first into broad sheets, then into narrower filaments, and finally into dense knots where those filaments intersected. In between, matter drained away, leaving growing voids. Over billions of years, the contrast sharpened. The dense regions became denser. The empty regions became emptier. The universe developed a kind of grand, slow anatomy. So when astronomers looked out at the galaxies and saw them tracing long thread-like structures, they were not just seeing a random arrangement. They were seeing the visible outline of a process billions of years in the making. They were seeing where matter had flowed. That idea is worth sitting with for a moment. Galaxies are often treated as isolated destinations, distant islands of stars. But in the cosmic web picture, they are also markers of motion. They tell a story about where matter gathered, where gravity guided it, and where the hidden scaffolding of dark matter had already set the stage. In a very real sense, the discovery of the cosmic web changed the role of galaxies in the story of the universe. They were no longer just objects floating in space. They became beads on invisible threads. And yet, even as the concept became more accepted, the web itself remained difficult to observe directly. Galaxies are bright enough to see. The gas between them is much fainter. Dark matter, of course, does not shine at all. So the web had to be inferred from different kinds of evidence, almost like recognizing the shape of wind by watching leaves move through it. Astronomers used galaxy positions, gravitational lensing, X-ray observations, and later more delicate methods to trace the matter lying between galaxies. They began finding signs of gas stretching along the filaments, hot and thin, hard to detect but clearly present. This was important. The cosmic web was not just an abstract pattern drawn by dots on a map. It was a physical structure. Matter truly did occupy those bridges between clusters. The web was real in substance, not only in geometry. That may sound obvious now, but at the time it was profound. One thing is to say galaxies appear aligned. Another is to prove that the space between them is filled with a meaningful cosmic medium, part of the same vast structure. As evidence accumulated, the web became more concrete. It was not merely the pattern of where galaxies happened to be. It was the framework in which galaxies lived and through which matter moved. There is a quiet thrill in that realization. The space between galaxies, which might seem empty and uninteresting at first glance, turns out to be part of the most enormous connected structure in existence. The emptiness is not simple emptiness. It has gradients, flows, boundaries, and threads. It belongs to the architecture. Another reason the term cosmic web became so compelling is that it captured something deeply visual without oversimplifying too much. A web suggests threads. It suggests intersections. It suggests tension and connectivity. And while the universe is not literally a spider's web, the comparison helped people imagine the right kind of large-scale shape. If you could somehow light up the matter of the universe and view it from a godlike distance, you would not see a featureless fog. You would see strands, knots, and hollow spaces. Still, the true discovery went beyond the image itself. It changed the questions cosmologists asked. Before, one major question had been how galaxies formed. After the Webb picture emerged, that question expanded. Now the deeper question became how the large-scale structure formed first, and how galaxies emerged inside it. The focus shifted outward. Instead of starting with individual galaxies and building up, cosmologists increasingly had to think in terms of the whole network. Where did the filaments come from? Why do voids grow? How does matter travel along the web? How do galaxy clusters form at the nodes where multiple filaments meet? What role does dark matter play at every stage? The discovery of the cosmic web did not tidy up cosmology. It made it richer. And this is one of the loveliest parts of science. A true discovery does not merely close a chapter. It opens a larger one. There was also something emotionally significant about the timing of all this. Humanity had already passed through several great demotions in its cosmic self-image. Earth was not the center of the solar system. The Sun was not the center of the galaxy. The Milky Way was not the whole universe. Then the universe itself turned out not to be a random scattering of galaxies, but a vast structured network in which our own galaxy occupied only one small location. Each step made the cosmos larger and our place within it more modest. And yet, at the same time, these discoveries made the universe feel more intelligible, not less. We were not lost in pure chaos. We were inside something shaped, something lawful, something with history. That balance between humility and understanding is part of what makes cosmology so calming. The scales are enormous, but the patterns are real. The universe is not arranged for our comfort, but it is arranged. It obeys principles that can be learned, slowly and patiently, with enough care. There is another subtle point in the discovery of the cosmic web that often gets overlooked. The web is not a finished sculpture. It is not a frozen object hanging motionless in space. It is an evolving structure. Matter continues to move through it. Galaxies interact with their location inside it. Clusters grow by drawing in material from surrounding filaments. Voids expand as matter drains away from them. The web is not just large. It is alive in the quiet cosmological sense, changing over immense timescales. That idea makes the discovery feel even stranger. Imagine looking at a map of river systems across a continent, only to realize the rivers themselves are still slowly carving the land. The cosmic web is not just where matter ended up. It is part of the process by which matter continues to organize itself. As observations improved in the 21st century, this picture became steadily sharper. Larger and deeper surveys mapped millions of galaxies. Simulations became more detailed. Gravitational lensing allowed astronomers to infer where dark matter lay by measuring how it bent the light from more distant galaxies. Piece by piece, the invisible portions of the web became less mysterious. Not fully visible, but less hidden. And still, even now, the web retains a dreamlike quality. It is one thing to understand it in theory. It is another to let the scale of it settle into your mind. The Milky Way, with all its stars, planets, dust clouds, and black holes, is only one tiny inhabitant of one small part of one filamentary structure in a vast cosmic network. Our entire local story, all of human history, every ocean, every mountain, every memory, takes place inside one small galaxy suspended in this greater arrangement. When you really let that thought in, it does something gentle to the mind. It widens the room. It loosens the grip of ordinary scale. Problems that feel close begin to soften a little when placed beside a web stretching across billions of light years. Perhaps that is one reason cosmic subjects can be so soothing at night. They do not erase what matters in human life, but they remind us that reality is much larger, much quieter, and much older than the noise of any single day. The discovery of the cosmic web also gave astronomers a new way to think about emptiness itself. Before, empty space might sound like a blank background, just the stage on which galaxies happen to exist. But once the web was recognized, empty space became more interesting. The voids were not passive leftovers. They were part of the pattern. They helped define the boundaries of the filaments and sheets. The contrast between fullness and emptiness became a central feature of the universe's design. In that sense, the web is not only made of matter, it is also made of separation. Threads matter because of the gaps around them. A filament looks like a filament only because the surrounding region is so much more empty. A node feels dense only because the surrounding cosmos is comparatively sparse. The architecture depends on both presence and absence, light and near darkness, crowded intersections and silent voids. It is a structure written in contrast. This is why, when people first see large-scale maps of the universe, they often describe them as beautiful. Not merely informative, beautiful. The web is scientifically important, of course, but it is also visually and emotionally striking. It looks like something nature would make if given enough time and enough gravity. Delicate from far away, immense up close, impossible to hold in one thought all at once. By now, the phrase cosmic web has become common in astronomy and science communication, but it is worth remembering how extraordinary that is. Humanity now has a name for the largest known pattern in the universe. Not just galaxies, not just clusters, but the network that links them. To name something is not to master it, but it does mark a step in our relationship with it. It means we have seen enough to recognize it as a thing in its own right. The cosmic web is one of those rare discoveries that reshapes both knowledge and imagination. Once you know it exists, the universe never looks quite the same again. Even the simple phrase, deep space, changes meaning. Space is not just depth. It is arranged depth. Not an endless blank, but a connected terrain of matter and emptiness. And the discovery was only the beginning. Because once astronomers accepted that the universe has this web-like design, a more intimate question naturally followed. What does that design actually look like when we slow down and examine its parts? What is a filament made of? How dense is a node? How empty is a void? If the web is real, then what are its textures, its boundaries, its components? That is where our journey moves next. But before leaving this part behind, it is worth resting once more with the discovery itself. Not just the data, not just the science, but the feeling of it. Imagine generations of astronomers patiently measuring faint galaxy light, building maps from almost invisible clues, and then realizing that the entire observable universe had been hiding an intricate pattern. A pattern too large to see directly, too quiet to announce itself, and too beautiful to remain unnoticed forever. The universe, it turned out, was not simply vast. It was woven. And that may be one of the most comforting ideas in all of cosmology. That beyond the darkness, beyond the distances, beyond the seeming loneliness of space, there is connection. Not the human kind, not the warm kind we know in ordinary life, but a deeper physical connectedness written into gravity and time. Galaxies belong to something. Clusters belong to something. Even the emptiest void belongs to the wider design. If this part of the journey has helped your mind drift into a quieter place, you can leave a gentle like, subscribe for more slow explorations of science, or share what part of the cosmic web feels most haunting to you so far. Is it the giant voids, the invisible dark matter scaffolding, or simply the idea that the universe has a hidden pattern at all? For now, let that pattern settle. Let the noise of the day move a little farther away. Somewhere above the Earth, beyond the stars we know by name, beyond the faint haze of the Milky Way, galaxies are arranged along threads so vast that they only reveal themselves to patience. And for a brief moment, from our small place inside it, we have begun to see the shape of the whole. Part 4: What the cosmic web actually looks like. Now that the hidden pattern has begun to reveal itself, a softer and more intimate question naturally follows. What does the cosmic web actually look like? not on a graph, not in a simulation for specialists, not as a dense page of numbers or a technical diagram full of labels, but in the mind, in imagination, in the quiet inner picture that forms when science stops being abstract and becomes something you can almost see. Because the phrase cosmic web is beautiful, but it is also slippery. It sounds familiar and strange at the same time. Most people hear it and picture a giant spiderweb hanging in the dark, glowing faintly in space. That image is not entirely wrong, but it is not quite right either. The real structure is less delicate than silk, less orderly than a wheel, and far more immense than any web we could compare it to. It is not symmetrical. It is not clean. It is not centered around anything. It is more like a living geography made of matter and emptiness, a vast architecture that only reveals itself when you zoom out far beyond any ordinary human scale. And that is the first thing to understand. The cosmic web is not a single object sitting somewhere in the universe. It is the large-scale pattern of the universe itself. If these slow journeys into the cosmos help you relax at night, you can gently support the channel with a quiet like or a soft subscription. And if you ever feel like leaving a comment, I always enjoy hearing which part of the universe feels most calming to you. Sometimes it is the stars, sometimes black holes, and sometimes it is simply the strange comfort of knowing that even emptiness has structure. To picture the cosmic web, it helps to begin with something simpler. Imagine a sponge. Not a perfect manufactured sponge with straight edges, but an irregular natural one, full of holes, tunnels, and thin walls separating open spaces. Now imagine that the thin walls of that sponge are made of galaxies, gas, and dark matter, while the holes are vast cosmic voids, regions with far less matter than average. That image gets us closer. Or imagine soap bubbles pressed together. The bubbles themselves represent enormous empty regions, and the matter of the universe lies mostly along the thin boundaries between them. Another image that works surprisingly well is the branching pattern of roots under the ground, or blood vessels spreading through a body, or even river systems seen from high above. There are thick channels, thinner branches, dense junctions, and long empty stretches in between. Nature often builds in networks. It does not usually arrange things in neat grids. It allows matter and flow to follow pressure, attraction, and time. The cosmic web belongs to that same family of natural patterns, except that its scale is so large that the mind resists it at first. What astronomers discovered is that when you map galaxies in 3 dimensions, they do not fill space evenly. Instead, they gather into long, thread-like structures called filaments. Where multiple filaments meet, matter piles up into dense intersections called nodes. And around these structures lie enormous regions of relative emptiness called voids. That is the web in its simplest form. Filaments, nodes, voids. These 3 parts are enough to sketch the whole architecture of the large-scale universe. Let's begin with the filaments, because they are the feature that gives the cosmic web its name. A filament is a giant thread of matter stretching across tens or even hundreds of millions of light years. It is not a solid thread, of course. You could travel through it and still pass through immense stretches of apparent emptiness. But compared with the surrounding voids, a filament is rich in structure. Galaxies line up along it. Gas drifts through it. Dark matter forms the invisible backbone beneath it. These are the cosmic highways, the great connective strands of the universe, linking one dense region to another. When people first imagine a filament, they sometimes picture a narrow glowing line, almost like a laser beam across space. In reality, a filament is broader, messier, and more complex. It can be millions of light years thick. It can twist, branch, and bend. It is not perfectly straight. It is more like a huge corridor of enhanced density, a river of matter that stretches across unimaginable distances. And inside that river are galaxies, galaxy groups, gas clouds, and invisible dark matter all participating in the same grand structure. If you could somehow stand far outside the universe and look at one filament from a distance, it might appear as a faint luminous thread. But if you moved closer, you would see that it is crowded with details. Hundreds or thousands of galaxies, streams of hot gas, regions where matter is slowly flowing along the filament toward a denser node. What seems like a simple line from far away becomes a richly textured environment up close. This is one of the recurring lessons of cosmology. Large structures often look simple only because they are so vast. Distance smooths complexity. The next major feature of the web is the node. A node is where filaments meet, where matter has gathered more strongly over billions of years. If filaments are the roads of the universe, nodes are the great intersections, the crowded cities, the hubs where traffic accumulates. These are often galaxy clusters or superclusters, places where gravity has drawn large amounts of matter into dense concentrations. A galaxy cluster can contain hundreds or even thousands of galaxies, all bound together by gravity. Their stars shine across a shared environment filled with extremely hot gas and enormous halos of dark matter. These places are among the most massive structures in the universe that remain held together as single systems. They are not peaceful in the gentle human sense. They are energetic environments where galaxies can interact, gas can be heated to astonishing temperatures, and gravity shapes everything around it. But from the vast perspective of the cosmic web, they are the bright knots where the threads come together. There is something deeply satisfying about nodes. In the maps of the universe, they make the web feel real. A pure network of thin lines might seem too abstract, too mathematical. But once those lines thicken into crowded intersections full of galaxies, the structure gains physical weight. You can almost feel gravity doing its work there, slowly and patiently, drawing matter inward over billions of years. And then there are the voids. The voids may be the most haunting part of the cosmic web, because they remind us that the universe is not only made of matter, but also of astonishing absence. A void is a huge region of space that contains far fewer galaxies than average. Not absolutely none, perhaps, but so few that compared with the rich boundaries around it, the region feels almost deserted. Some voids span tens of millions of light years. Others stretch for hundreds of millions. There are supervoids so large that even saying the number aloud barely helps. These are not just empty corners. They are major features of the cosmic landscape. In fact, much of the universe by volume is made of these underdense regions. The web occupies the edges. The voids occupy the wide interiors. This is why the sponge analogy is so useful. The visible filaments and nodes are important, but much of the overall shape comes from the holes between them. The universe, on its largest scales, is less like a solid block of matter and more like a framework surrounding enormous empty chambers. And once you picture that clearly, the beauty of the web becomes much easier to feel. Imagine floating through a region of the universe deep inside a void. Far in every direction there would still be galaxies, but fewer of them, more isolated, less richly connected. The darkness would feel wider. The nearest major filament might lie tens of millions of light years away. Matter would be sparse. The sense of structure would be faint. Then imagine traveling toward the boundary of that void. Slowly, the galaxy density would increase. Small groups would become more common. Then chains would appear. Then longer threads. Eventually you would arrive at a filament, a corridor of matter running across space like a barely glowing bridge. If you followed that bridge long enough, it would lead you toward a node, a place where multiple filaments converge and gravity has gathered galaxies into dense company. That journey, from void to filament to node, is one of the best ways to understand what the cosmic web actually looks like. It is a transition from emptiness to connection, from silence to structure. There is another subtle point that makes the web easier to picture. The galaxies we see are only the bright part of the story. Most of the web is not made of shining starlight. Much of it is dark matter, invisible but gravitationally dominant, along with extremely thin gas spread through intergalactic space. In other words, the web is mostly hidden. What our telescopes see most clearly are the luminous markers, the galaxies and hot gas that reveal where the invisible scaffolding lies. That means the web is not like a fully lit city at night. It is more like a dim framework traced by occasional lanterns. The galaxies show us where the structure is, but they do not make up the whole of it. They are the visible hints of something much larger and mostly unseen. There is something dreamlike about that idea. The universe's true large-scale form is present all around us, but most of it cannot be seen directly. We infer it. We trace it through clues. We map it through light bent by gravity, through the positions of galaxies, through the faint glow of gas stretched between clusters. The cosmic web is one of the clearest examples in science of how the hidden can still be known. And perhaps that is part of why it feels so powerful. It speaks to the quiet human instinct that reality has layers. The visible layer is only the beginning. When astronomers build visualizations of the cosmic web, the result often looks almost biological. The filaments branch and connect in patterns that can remind people of neurons in a brain, or fungal networks in a forest, or the circulation system of a living body. These comparisons should not be taken too literally. The universe is not a brain, and the web is not a conscious system. But the resemblance is striking because the same broad principles often shape complex structures in nature. Matter flows. Gravity gathers. Networks emerge. The details differ, but the pattern of connection appears again and again. If anything, these comparisons help us emotionally rather than scientifically. They make the cosmic web less sterile, less distant. They remind us that the universe is not just made of isolated objects, but of relationships. One place links to another. Matter travels. Gravity connects. The shape of the whole matters. Another helpful way to imagine the web is to think about coastlines on a global map. If you color only the continents and leave the oceans dark, the Earth reveals a very clear pattern of boundaries and spaces. Now reverse the idea. In the cosmic web, the continents are not solid land but the filaments and nodes, while the oceans are the voids. The universe becomes a geography of presence and absence, where the most important features are not individual galaxies but the way galaxies outline vast regions around them. This is also why the term structure keeps appearing in cosmology. The cosmic web is not just decoration. It is structure in the deepest sense. It tells us where matter collected, where galaxies formed, how clusters grew, and how the universe evolved from tiny early fluctuations into the immense patterned cosmos we observe now. To describe what the web looks like is also, in some sense, to describe what the universe has been doing for billions of years. And yet the web is not perfectly fixed. Its shape changes slowly as matter continues to move. Galaxies fall toward dense regions. Clusters grow by accreting matter from connected filaments. Voids become emptier as more material drains away from them. So the web is not a frozen diagram. It is a slow-motion structure, changing on timescales so vast that human life cannot witness the movement directly. That can be strangely calming to think about. Somewhere in the deep cosmos, matter is still drifting along filamentary paths, still gathering into nodes, still leaving behind wider emptiness in the voids. The universe is not rushing, but it is not still either. It is patiently rearranging itself. Now, if we zoom in a little more closely on the filaments, something even more interesting appears. Filaments are not all the same. Some are thicker, richer, more heavily populated with galaxies. Some are thinner and more subtle. Some connect major clusters. Others branch off into smaller groupings. They form a hierarchy of structure. A bit like roads. There are major highways, minor routes, side paths, and local connections. The large-scale pattern is coherent, but not uniform. The same is true of nodes. Some nodes are modest intersections, home to smaller galaxy groups. Others are truly enormous clusters containing staggering amounts of mass. These dense nodes often sit at the meeting point of multiple filaments, as though the geometry of the web is funneling matter into them from several directions at once. And the voids, too, are not all identical. Some are relatively small gaps between denser structures. Others are immense regions of underdensity, so large that they challenge our instinct for cosmic proportion. A void is not simply empty space left over by accident. It is part of the dynamic evolution of the large-scale universe, a place from which matter has been steadily drawn away. This richness of variation matters because it keeps the cosmic web from becoming too simple in the mind. It is not one neat repeated motif stamped across the universe. It is a real natural pattern, irregular, layered, and alive with differences. The more you think about it, the more the web begins to feel less like a picture and more like a terrain. Not a terrain of solid ground, but of density. Thick and thin regions, junctions and stretches, hollow chambers and crowded boundaries. If you could somehow travel through it at impossible speed, your experience of the cosmos would change depending on where you were. In a void, the universe would feel more isolated and sparse. In a filament, it would feel gently connected. In a node, it would become crowded, luminous, and gravitationally intense. Our own galaxy, the Milky Way, lives within this terrain too. We are not outside the web looking at it from a safe distance. We are inside it, passengers within one local thread of a much greater design. That can be hard to hold in the mind because human scales are so small, but it is true. Everything we know takes place inside one tiny part of the cosmic web. The Earth, the Moon, the Sun, the Milky Way, our local galactic neighborhood, all of it sits somewhere inside this immense structure of filaments, nodes, and voids. And this brings us to one of the most comforting images in all of cosmology. The universe is not just a black emptiness sprinkled with random lights. It has shape. It has pathways. It has crowded intersections and quiet regions. It has a hidden architecture that gives place to galaxies and context to everything we see. Once you understand that, the cosmos stops feeling like pure scatter and starts feeling like something woven. That word matters. Woven. Because weaving suggests relation. It suggests tension between parts, threads crossing and supporting one another, a fabric that gains meaning from connection. The cosmic web is not literally fabric, but the metaphor captures something essential. Galaxies are not alone. They are part of a greater weave of matter and gravity extending across the observable universe. If you ever feel overwhelmed by the size of cosmic ideas, it sometimes helps not to focus on the numbers first. Focus on the shapes. The web is easier to understand visually than mathematically. Long filaments, bright knots, great dark voids. That is the large-scale universe in a form the mind can carry gently. And once the image settles, the numbers can return later with more meaning. Because when someone says a filament may stretch for hundreds of millions of light years, that number lands differently once you already picture it as one thread in a vast connected structure. When someone describes a galaxy cluster containing hundreds or thousands of galaxies, it feels different once you imagine it as one glowing knot in the weave. When someone mentions a void spanning a huge region of space, the number becomes more haunting once you have already felt the emptiness around the web. This is why Part 4 matters so much in the larger flow of the script. Before we move deeper into size, scale, and formation, we need the inner picture to feel real. We need to know what we are looking at. So let it settle again. The cosmic web is made of filaments, long thread-like structures rich in galaxies, gas, and dark matter. It is marked by nodes, the crowded intersections where those filaments meet and matter grows dense. And it is shaped by voids, the enormous underdense regions that surround the luminous boundaries and give the whole structure its haunting form. Together, these features create the universe's large-scale appearance, a sponge-like, lace-like, root-like network stretching across unimaginable distances. And still, there is something almost gentle about it. Not gentle in scale, of course. The scale is overwhelming. But gentle in the sense that the structure is not violent to imagine. It does not demand noise or urgency. It invites stillness. The web is a slow geometry. A patient design built over billions of years. It does not flash into being. It gathers. It stretches. It empties. It connects. Perhaps that is why it is such a perfect subject for the quiet edge of sleep. The cosmic web does not feel like a shout from the universe. It feels like a long breath. If this part of the journey has helped your mind slow down, you can leave a soft like, subscribe for more calm science stories, or tell me in the comments which image stays with you most: the glowing filaments, the dense cosmic nodes, or the enormous silence of the voids. Sometimes the comment section on a sleepy science video becomes its own small map of connection, people from different places quietly meeting under the same idea. And as we drift onward, one question naturally remains. If this is what the web looks like, then just how large are its individual pieces? How long can a filament become? How big are the largest nodes? And how empty, truly, are the voids that fill so much of the cosmic landscape? That is where the scale begins to stretch even further. One quick note before we continue later: some of the earlier uploaded reference files have expired on my side. I can keep matching the style from what we've already built in this chat, but if you want me to recheck the original uploaded files directly again later, just upload them once more. Part 5. How large is one cosmic filament? If the cosmic web is the hidden architecture of the universe, then its filaments are the long, dim corridors that give that architecture its shape. They are the threads between the great intersections, the bridges between crowded regions of galaxies, the quiet pathways along which matter has been moving for billions of years. And once you begin to ask how large a single filament can be, the answer starts to stretch the imagination in a very peaceful and unsettling way. Because a filament is not just big, it is the kind of big that makes even a galaxy feel small. If these slow explorations of the universe help you settle into the night, you can gently support the channel with a like or a quiet subscription. And if you feel like leaving a comment, I always enjoy hearing what part of space feels most mind-bending to you. Sometimes it is black holes, sometimes time, and sometimes it is simply the realization that a galaxy can be just one tiny piece of a much larger thread. To understand the size of a cosmic filament, it helps to begin with something familiar. Our Milky Way galaxy is already enormous by human standards. It is roughly 100,000 light-years across. That means even light, moving faster than anything else in the universe, would need 100,000 years to cross the visible width of our galaxy. Human history looks almost invisible beside that timescale. And yet, in the language of the cosmic web, the Milky Way is not a filament. It is not even close. It is more like one bright city along a vast route. One localized concentration of stars inside a much larger structure. A single filament can stretch for tens of millions of light-years. Some extend for around 50 million light-years. Others can reach 100 million light-years or more. And in some cases, astronomers see connected structures that span several hundred million light-years, sometimes even approaching a billion light-years when the broader arrangement of matter is considered. At that point, numbers begin to lose their natural meaning. So instead of rushing past them, it is worth slowing down and letting the scale unfold gradually. Imagine the Milky Way shrunk down in your mind to something manageable. Not physically, of course, but conceptually. Imagine it as one tiny glowing grain inside a long, faint thread. Now imagine another grain far beyond it, and another, and another. The spaces between them are not small. They are often millions of light-years wide. Yet all of them belong to the same filamentary structure, the same extended corridor of galaxies, gas, and dark matter. The thread continues long after any single galaxy disappears from view. This is one of the most important things to understand about a filament. It is not a single visible beam. It is not a neatly outlined object with sharp edges. It is a region of the universe where matter is more concentrated than in the surrounding voids, and where that matter traces a long, connected path. Galaxies may appear along it like scattered lanterns in fog. Between them lies intergalactic gas, and beneath everything lies the dominant invisible scaffolding of dark matter. A filament is immense, but much of that immensity is quiet and faint. That faintness matters, because it helps explain why the size of a filament is so hard to feel emotionally at first. If a filament were a glowing rope blazing across the cosmos, it would be easier to imagine. But in reality, much of it is subtle. Much of it must be inferred. The galaxies provide clues. The gas adds a trace of presence. The dark matter does most of the real structural work, but it remains unseen except through gravity. So when we ask how large a filament really is, we are asking about a structure that is bigger than what our eyes can directly capture. And that makes it all the more haunting. It means the universe's great connective threads are not only vast, they are mostly hidden. A useful comparison is the distance between the Milky Way and the Andromeda Galaxy, our nearest large galactic neighbor. That gap is about 2.5 million light-years. On ordinary astronomical scales, that is already enormous. It is enough to make the space between galaxies feel practically endless. But a filament can run for tens of millions of light-years, sometimes much more. So even if you lined up the distance to Andromeda again and again and again, you would still only be tracing a small portion of one cosmic thread. Another way to think about it is this. If the Milky Way is about 100,000 light-years across, then a filament that spans 50 million light-years is roughly 500 times longer than our galaxy is wide, and many are longer still. A 100 million light-year filament would be around 1,000 times the width of the Milky Way. This is where the scale becomes quietly absurd. We are no longer talking about a structure that contains galaxies. We are talking about a structure that makes galaxies look like minor features along its length. And yet, despite that size, filaments are not empty passageways. They are active environments in the long, slow sense of cosmic time. Matter flows through them. Gas travels along them. Galaxy groups gather within them. Clusters at their ends or intersections feed on the matter drifting down these enormous lanes. A filament is not just a static thread hanging in darkness. It is more like a current. This image becomes even more powerful when we think about what a filament is made of. The most obvious part, at least from our perspective, is the galaxies. Those are the visible markers, the lights we can map. But galaxies are only the bright punctuation marks. Most of the matter in a filament is not locked up in stars. A great deal of it exists as diffuse gas spread thinly across intergalactic space. And even more of its total mass is thought to be dark matter, the invisible component whose gravity shapes the web. The gas inside filaments is especially interesting because for a long time, much of it was difficult to detect. Astronomers suspected it had to be there. The numbers told them that a large fraction of ordinary matter in the universe seemed to be missing from easy observation. Over time, evidence accumulated that much of this so-called missing baryonic matter was not truly missing at all. It was spread through the filaments as a very thin, very hot medium, often called the warm-hot intergalactic medium. That phrase sounds technical, but the basic idea is simple. Space between galaxies is not always truly empty. In many filaments, it contains a ghostly gas, heated to extreme temperatures, stretched across enormous distances, and so diffuse that even a vacuum created in a laboratory would feel crowded by comparison. The density can be extraordinarily low, just a handful of particles in a volume that, by everyday standards, feels impossibly large. And yet, because the filament itself is so vast, that faint gas adds up to an enormous amount of matter. There is something beautiful about that. A structure can be almost unimaginably empty on a local scale and still enormously substantial when viewed across millions of light years. Emptiness, in cosmology, is rarely simple. And that brings us back to the central question: how large is one cosmic filament really? The honest answer is that there is no single standard size. Filaments come in different lengths and thicknesses. Some connect nearby clusters. Some stretch across much larger regions. Some are modest by cosmic standards. Others are among the largest recognizable features in the large-scale universe. But even a relatively ordinary filament is still staggeringly immense. If you could travel along one at the speed of light, your journey could take tens of millions of years. Not days. Not centuries. Not even the age of human civilization multiplied many times over. Tens of millions of years, just to follow the span of a single cosmic thread. That kind of distance softens the mind a little if you sit with it long enough. It reminds you that the universe builds on scales completely detached from ordinary experience. Our instincts are not built for it. Human life is measured in years. Human travel is measured in miles and hours. Even planetary distances, once they become very large, already feel abstract. But the filament asks more of us. It asks us to imagine a bridge so long that whole eras of life on Earth could begin and end while a beam of light is still making its way from one end to the other. And then it asks us to remember that the filament itself is only one thread inside the wider cosmic web. Some of the most famous large-scale structures astronomers have identified are essentially made of filaments and related connected arrangements. The Sloan Great Wall, for example, is often described as one of the largest structures ever found in the distribution of galaxies, extending across more than 1 billion light-years. The exact way scientists define such a structure can vary, and not every part of it is a single simple filament. But discoveries like this help reveal just how far large-scale patterns can extend. The universe is not modest with its architecture. Once matter begins to organize itself on the largest scales, it can create features that seem to press against the limits of our sense of proportion. Still, I think there is something more calming in focusing on one filament rather than only the very largest named structures. A single filament is enough to overwhelm the imagination. It is enough to carry the mind away from ordinary scale. You do not need the most extreme example for the truth to feel astonishing. One long thread of matter, tens of millions of light years in length, already changes the way the universe feels. It also changes the way galaxies feel. A galaxy is not small in any absolute sense. The Milky Way contains hundreds of billions of stars. It holds planets, nebulae, black holes, star clusters, and vast clouds of gas and dust. It is a world of worlds. But beside a filament, a galaxy becomes local, provincial. One bright neighborhood along a route much older and larger than itself. There is a quiet humility in that image. We often speak of galaxies as if they are final destinations, the major landmarks of the cosmos. But the filament reminds us that galaxies themselves belong to a higher order of structure. They are not merely suspended in emptiness. They live along corridors shaped by gravity and dark matter. They inherit their environment from something much larger. This is one reason cosmologists care so much about filaments. They are not just decorative features on a map. They help shape how galaxies grow. Gas can flow along them toward denser regions, feeding galaxy groups and clusters. Galaxies within or near filaments may experience environments different from those deep inside voids. The filament is not only big, it is influential. It is part of the universe's supply system, its transport network, its long connective tissue. Even the word thread starts to feel more meaningful here. A thread does not merely occupy space. It connects places. It carries tension. It belongs to a wider fabric. That is exactly what a filament does in the cosmic web. It links dense nodes across enormous distances, carrying matter across the universe's largest known network. And if you picture many of these filaments at once, the web becomes easier to feel. Not a single isolated bridge, but countless long strands stretching across the observable universe, intersecting, branching, surrounding voids, and creating the deep sponge-like pattern we talked about earlier. One filament is already vast beyond comfort. Many filaments together become almost impossible to hold in a single thought. There is another part of the story that makes filaments even more interesting. Some evidence suggests that these structures are not entirely passive. In recent years, astronomers have found signs that certain cosmic filaments may show large-scale rotational behavior, a kind of slow twisting motion on scales far bigger than anyone once expected. This is still an area of active study, but the idea itself is mesmerizing. A filament is not just a line of matter. It may be a slowly evolving, subtly dynamic channel in the web, not frozen, but moving in deep time. That possibility changes the emotional texture of the filament. It becomes less like an ancient road and more like a river. Still slow beyond belief, but not dead. Still shaping and being shaped across cosmic ages. Now let's come back to the human side of all this, because the numbers alone can become too dry if we are not careful. The real wonder of a filament is not just that it is long. It is that its length transforms perspective. Think about the distances we use in daily life. A city might feel large. A country might feel enormous. Even the Earth itself, seen from the ground, can feel effectively endless. Then we learn the Earth is tiny compared with the Sun, and the Sun is tiny compared with the Milky Way. Then the Milky Way turns out to be just one galaxy among many. And then the filament arrives and quietly pushes the scale outward again. It says that even galaxies come arranged inside structures vastly larger than themselves. That is a very gentle kind of cosmic shock. Not the sharp, frightening kind. More the kind that loosens the grip of the familiar and lets the mind drift into larger waters. When people struggle to imagine the cosmic web, it is often because they try to jump straight from human scale to universal scale in one motion. But the filament gives us a middle step. It is bigger than a galaxy, smaller than the whole web, and therefore perfect for widening the imagination one layer at a time. First comes the star system, then the galaxy, then the filament, then the cluster, then the wider web. Each step does not erase the previous one, it places it, and placement matters. A galaxy means one thing alone. It means something deeper when you know it belongs to a filament. The Milky Way becomes not just our home galaxy, but part of a greater large-scale arrangement. It becomes one local expression of a cosmic geography extending far beyond anything the naked eye can reveal. Perhaps that is why filaments feel so haunting. They are not flashy like exploding stars or mysterious like black holes. They do not shout for attention. They are too large and too patient for that. Instead, they offer a quieter kind of wonder. The wonder of connection. The wonder of hidden structure. The wonder of realizing that the darkness between the brightest things is not blank, but organized. And maybe that is the deeper answer to how large one filament really is. Its size is not only measured in millions of light years. It is measured in the way it changes the meaning of everything inside it. It turns galaxies into local features. It turns empty space into a corridor. It turns the universe from a scatter of objects into a network of relationships. That is the emotional size of a filament. And in the hours before sleep, that may be the gentlest way to understand it. A filament is a road of matter so long that light itself needs millions upon millions of years to cross it. It is a dim river of galaxies, gas, and dark matter connecting the dense knots of the cosmic web. It is broader and richer than a simple line, subtler than a glowing beam, and far more immense than ordinary language likes to admit. Some are tens of millions of light years long. Some are longer. All of them remind us that even the grandest galaxies live inside something larger. If this part of the journey has helped your mind drift a little farther from the day behind you, you can leave a quiet like, subscribe for more calm science stories, or tell me in the comments what comparison helps you feel the scale most clearly. The Milky Way against a filament. The distance to Andromeda repeated again and again. Or the thought of light spending tens of millions of years traveling one cosmic thread. And as we continue, the scale is only going to widen. Because if one filament is already so vast that galaxies become almost secondary along its length, then what happens when many filaments join together into the greatest structures astronomers have ever found? How large can those intersections and walls become? And at what point does cosmic structure begin to challenge even the theories we use to describe the universe? That is where the story becomes even stranger. And one small note so we stay aligned: I can keep matching the established tone from the parts we've built here. Some of your earlier uploaded reference files have expired on my side, so if later you want me to recheck those originals directly, just upload them again. Part 6: The largest structures ever found. If one cosmic filament is already so large that the Milky Way begins to feel like a tiny local detail, then the next question arrives almost automatically, and it arrives with a certain quiet force. What happens when many of those filaments connect? What happens when the web thickens, stretches, and gathers itself into structures so large that even astronomers pause before naming them? This is where the universe begins to feel almost unreasonable. Because the largest structures ever found are not simply bigger than galaxies. They are not just bigger than clusters, or even bigger than the long filaments we have been talking about. They are so large that they push directly against our instinct for proportion. They begin to challenge not only the imagination, but sometimes even the assumptions scientists use to describe the universe on its grandest scales. And yet, as dramatic as that sounds, this part of the story is best approached slowly. Not as a list of giant cosmic objects, but as a gentle widening of perspective. We are not leaving behind the calm logic of the cosmic web. We are simply following it farther than comfort likes to go. If these slow journeys through space help you settle into sleep, you can quietly support the channel with a like or a soft subscription. And if you feel like it, leave a comment telling me which cosmic scale feels most unreal to you so far. A galaxy, a filament, a void, or these enormous structures that seem to stretch almost beyond the limits of what structure should be. To understand the largest structures in the universe, it helps to begin with something important and surprisingly simple. When astronomers say, largest structure, they do not always mean a single solid thing. They usually mean a vast connected arrangement of galaxies, clusters, and filaments. A large-scale pattern. A region where matter is more densely organized than the surrounding cosmos, and where that organization continues across astonishing distances. That means these structures are not like giant planets or giant stars. They are not compact. They do not have hard edges. They are often web-like, sprawling, and subtle. Their size is measured not by a solid boundary, but by how far the coherent pattern extends. That matters, because without that idea, the numbers can feel misleading. If someone says a structure is hundreds of millions of light years long, or even more than a billion, the mind might imagine some enormous glowing object floating intact through space. But the reality is gentler and stranger than that. These structures are often more like cosmic continents than cosmic balls. More like long ridges, walls, or connected networks than simple objects. One of the most famous examples is the Sloan Great Wall. The name itself has a kind of grandeur to it, and in this case, the grandeur is deserved. The Sloan Great Wall was identified using data from the Sloan Digital Sky Survey, one of the great mapping efforts in modern astronomy. It revealed an immense arrangement of galaxies stretching across roughly 1.3 to 1.4 billion light years. Even saying that slowly does not make it easier to feel. A billion light-years is already the kind of distance that weakens ordinary thought. A structure spanning more than that feels almost too large to belong inside a universe that is supposed to be orderly. And yet there it was in the data. Not a solid slab, not a simple line, but a vast connected feature in the large-scale distribution of galaxies. The word wall is useful here, even if it is imperfect. It captures the impression astronomers had when these giant arrangements first became visible. They did not look like tidy clusters. They looked like immense sheets or ridges, as though matter in the universe had settled into colossal boundaries separating larger empty spaces. A wall suggests something extended, something that cuts across the map in a dramatic way, and that is exactly the emotional effect these structures produce. Before the Sloan Great Wall, another famous discovery had already prepared astronomy for this kind of surprise. That earlier structure was called, simply and appropriately, the Great Wall. It was found in galaxy survey data in the late 20th century and extended across about 500 million light-years. At the time, this was breathtaking. It helped confirm that the universe contained structures much larger than anyone had comfortably expected. It was one of the discoveries that pushed the idea of the cosmic web from possibility into reality. And then, as so often happens in science, the record did not stand forever. Larger surveys revealed larger patterns. Better maps allowed broader connections to appear. What once seemed like the most extreme structure in the known universe became, over time, one example among several. Not because it had become less impressive, but because the universe kept revealing even more ambitious architecture. That, in itself, is a quietly lovely thing. The cosmos does not stop at the edge of our expectations. It almost never has. There are other named structures too, some of them less famous outside astronomy, but just as haunting when you sit with them. The Pisces-Cetus supercluster complex is one example, a huge connected arrangement of galaxy clusters and filaments stretching across an enormous region. These names can sound a little technical at first, but beneath them lies a simple truth. The universe is capable of building features on scales so large that naming them becomes an act of surrender as much as description. We call them walls, complexes, superclusters, groups. We try to fit language around them, but what really matters is the scale. And then there is one of the strangest and most debated examples of all, the Hercules Corona Borealis Great Wall. Even the name feels almost impossibly long, as though language itself is struggling to contain the size of the thing. This proposed structure was inferred using the distribution of gamma-ray bursts, those immensely powerful flashes associated with extreme cosmic events in distant galaxies. When astronomers looked at where these bursts appeared across the sky and at what distances, they found a clustering pattern that suggested something astonishing. It seemed possible that there was an enormous large-scale structure spanning roughly 10 billion light-years. 10 billion. That number lands differently when you say it slowly. Not 10 million. Not a few hundred million. 10 billion light-years. If that estimate truly reflects one coherent structure, it would represent one of the largest known patterns in the universe by far. So large, in fact, that it begins to disturb a key idea in cosmology known as the cosmological principle. This principle, in very gentle terms, says that on the largest scales, the universe should be more or less uniform. Not identical in every small place, of course, but smooth when averaged over great enough distances. Local structures can exist. Clusters can exist. Filaments can exist. Walls can exist. But eventually, if you zoom out far enough, the universe should stop showing such dramatic irregularities. A 10 billion light-year structure is the kind of claim that makes cosmologists sit up very carefully. And this is where the story becomes more subtle, and perhaps more beautiful. Not every large structure claim is accepted without question. Astronomy is full of patterns, but human beings are also very good at seeing patterns, even when the pattern may be more fragile than it first appears. Data can be limited. Selection effects can distort the picture. Boundaries can be hard to define. Some astronomers argue that the Hercules Corona Borealis Great Wall may not be one single coherent object, but rather a statistical clustering, a pattern that looks more unified than it truly is. That uncertainty is not a weakness in science. It is part of the calm honesty of the process. The universe does not owe us easy answers. And scientists, at their best, do not rush to certainty simply because a result is exciting. They test. They doubt. They compare. They ask whether the pattern is real, or whether it is a temporary shape in limited data. So when we speak of the largest structures ever found, we are also speaking of an active frontier, a place where observation and caution move together. In a strange way, that makes the story even more soothing. It reminds us that cosmology is not only about giant claims. It is about patient listening. There are other debated giants too. One well-known example is the Huge Large Quasar Group, sometimes shortened to Huge LQG. Quasars are among the brightest objects in the universe, powered by material falling into supermassive black holes at the centers of distant galaxies. When astronomers noticed an enormous grouping of quasars spread across a tremendous distance, it raised similar questions. How large can real cosmic structure become before it starts to strain the assumptions of large-scale uniformity? Where is the line between a meaningful structure and a chance arrangement that only appears significant from our limited point of view? These are not small questions. They go right to the heart of how we describe the universe itself. Because on one hand, the cosmic web clearly exists. Its filaments, nodes, and voids are real features of large-scale structure. But on the other hand, cosmology also tells us that if we zoom out far enough, those structures should blend into an overall smoothness. The universe should have texture, yes, but not unlimited irregularity at every possible scale. There should be a transition point where the web, magnificent as it is, gives way to statistical sameness. So every time astronomers find another colossal wall, cluster complex, or quasar grouping, they are not just adding another big object to a list. They are testing the boundary between structure and uniformity. They are asking how long the universe keeps its visible architecture before that architecture dissolves into the larger average. That makes these giant structures scientifically important in a deep way. They are not simply extreme examples. They are measurements of the universe's willingness to remain patterned. And if you step back from the science for a moment, there is something deeply mesmerizing about that. The universe seems to organize itself in rich, elaborate ways across scales that feel almost impossible, and then, beyond some still larger scale, it softens into smoothness again. Structure emerges, grows, stretches, and finally begins to disappear into statistical calm. It is almost like breathing. Density and emptiness, form and uniformity, complexity and simplicity, all nested inside one another. Let's slow down with one of these examples for a moment, because sometimes numbers become easier to feel through comparison. The Milky Way is about 100,000 light-years across. A large filament may stretch tens or hundreds of millions of light-years. A giant wall like the Sloan Great Wall extends beyond 1 billion light-years. The observable universe is roughly 93 billion light-years in diameter. So even these enormous structures occupy only a fraction of the whole observable cosmos. Yet that fraction is still so large that it transforms how we think about cosmic geography. A billion light-year wall is not just big. It is big relative to the very map of the observable universe that human beings have painstakingly assembled. It becomes one of the major visible strokes in the cosmic landscape, one of the huge brush marks in the universe's large-scale painting. And yet these structures are not floating alone in isolation. They are embedded within the web. They arise from it. A wall is not separate from the filamentary universe. It is one way the web appears when matter collects over enormous scales in a connected pattern. This is why the story remains coherent. We are not suddenly leaving behind the cosmic web and entering a new kind of universe. We are simply following the web into its most extravagant visible expressions. That continuity matters for the tone of this journey. We are not collecting monsters. We are tracing architecture. Another reason the largest structures feel so haunting is that they exist at the border of what language can comfortably describe. Terms like supercluster and wall help, but they also slightly fail. They were invented by human beings whose minds evolved to think about forests, weather, faces, paths, rivers, and seasons, not billion light-year patterns in the galaxy distribution of the observable universe. So there is always a quiet mismatch between the scale of the thing and the scale of the words used to name it. Maybe that is part of the magic. A wall, in daily life, is something you can touch. In cosmology, a wall can stretch across distances so vast that all of human civilization could rise and vanish many times over while light is still crossing it. A cluster, in daily life, sounds small and close. In cosmology, a cluster can contain hundreds or thousands of galaxies. A group sounds intimate. A quasar group can sprawl across scales that make even other cosmic structures look modest. The universe keeps borrowing our little words and filling them with enormous meaning. There is also something important to remember about how these giant structures are found. They are discovered in maps, not in one grand image, not by a traveler drifting past them. They emerge from data, from many distant galaxies plotted in 3 dimensions, from statistical patterns in light reaching us across deep time. In other words, the largest structures in the universe are not obvious to ordinary perception. They are visible only through patience, measurement, and perspective. That is such a gentle scientific lesson. Some truths are too large to see directly. You only find them when enough small observations are gathered together. A single galaxy reveals almost nothing about a wall. A few clusters reveal very little. But tens of thousands, then millions of galaxies mapped over large regions of space, and suddenly the pattern begins to show itself. The structure appears not because it changed, but because our perspective widened enough to notice it. That widening is, in some sense, the emotional center of the whole cosmic web story. At every step, reality becomes less random and more interconnected as our map improves. First galaxies, then clusters, then filaments, then walls, then immense debated structures that brush against the scale where smoothness should begin to take over. And every one of those steps teaches the same quiet thing. The universe has deeper order than it first seems. Still, there is a limit. Or at least, there should be. Cosmologists often speak about a scale beyond which the universe becomes homogeneous, meaning that the great structures average out and no further meaningful pattern persists in the same dramatic way. This is sometimes informally described as the point where the universe stops looking like a web and begins to look smooth again. If that picture is right, then even the largest structures ever found are not infinite. They are not the whole story. They are the most expansive visible features within a larger cosmos that becomes simpler when viewed broadly enough. That idea is strangely comforting. However immense the great walls may be, they are still part of a universe that eventually softens into balance. The cosmos allows complexity, but not without limit. And yet, because we are human, we remain fascinated by the giants near that boundary. We want to know what the largest thing is. We want to ask whether the latest discovery breaks the rule. We want to know whether the universe is a little wilder than our theories expected. That curiosity is natural. It is part of what keeps cosmology alive. But in the quiet atmosphere of this script, what matters most is not the competition of record-breaking sizes. It is the feeling these structures leave behind. They remind us that the universe is not merely full of objects. It is full of relationships extending across astonishing distances. The great structures are not just big, they are connected. Their size is the size of linked matter, of repeated influence, of gravity writing patterns across space over billions of years. That is a very different kind of bigness from a star or even a galaxy. It is architectural bigness, structural bigness, the bigness of geography rather than the bigness of a single body. And geography is always calming in its own way, because it gives things place. Even the largest structures ever found are, in the end, locations within the wider map. They help us understand where the densest regions lie, how matter gathered, how the web stretched itself across the observable universe. They are giant landmarks in a terrain so vast that the mind can only touch it in fragments. Perhaps that is enough. We do not have to fully grasp the scale for it to work on us. We only have to let it widen the room a little. Imagine drifting outward, far beyond the Milky Way, far beyond the local group, far beyond nearby clusters, until the great filaments of the universe begin to resolve. Then drifting farther still, until some of those filaments seem to gather into colossal ridges and vast connected features. And farther still, until even the great walls become parts of a broader map, and the map itself starts to blur into something smoother and more uniform. That long transition, from local galaxy to giant wall to eventual cosmic sameness, is one of the most beautiful gradients in science. It reminds us that size in the universe is layered. There is always another scale above the one we just learned to understand. If this part of the journey has helped your mind loosen a little from ordinary scale, you can leave a quiet like, subscribe for more slow explorations of science, or share in the comments which giant structure lingers in your mind most. The Great Wall, the Sloan Great Wall, or the almost unbelievable possibility of something like the Hercules Corona Borealis Great Wall stretching across a huge fraction of the visible universe. And as we continue, the natural question becomes even larger still. If the universe can build structures this vast, then what is the size of the whole pattern they belong to? Not one wall, not one filament, not one cluster complex, but the cosmic web itself across the observable universe. How far does the web really extend when we stop thinking locally and start thinking about the entire visible cosmos? That is where the scale opens all the way. And one small note so we stay aligned, I'm continuing in the same established tone from the parts we've already built together here. Some of the older uploaded reference files have expired on my side, so if later you want me to directly recheck those originals again, just upload them once more. Part 7, the true size of the entire cosmic web. By the time you reach the largest walls, clusters, and superstructures ever found, something curious begins to happen to the mind. At first, each new scale feels like the final one. A galaxy already seems impossibly large. Then a cluster makes the galaxy feel local. Then a filament makes the cluster feel like one stop along a road. Then a great wall stretches across such distances that even the filament begins to seem like only one detail in a much greater design. And naturally, after all of that, a deeper question rises very softly in the darkness. If these are only pieces of the web, then how large is the whole thing? Not one filament, not one cluster, not one wall, but the full web of structure across everything we can see. That is where the scale opens into its final form, and where language begins to feel a little too small for the task. If these slow journeys through science help you drift into sleep, you can quietly support the channel with a gentle like or a soft subscription. And if you feel like it, you can leave a comment telling me which cosmic number feels hardest to picture. Sometimes one simple number can stay with the mind for a long time, especially when it begins to change the way the whole universe feels. To understand the true size of the cosmic web, we first need to separate two ideas that sound similar but are not quite the same. One is the size of the universe itself, which may be far larger than anything we can observe, and may even be infinite. The other is the size of the observable universe, the region from which light has had enough time to reach us since the beginning of cosmic expansion. When astronomers talk about the large-scale structure we can map, they are talking about the observable part, the universe that lies within our cosmic horizon. And that horizon is already overwhelming. The observable universe is often described as being about 93 billion light-years across. That number can sound confusing at first. If the universe is around 13.8 billion years old, why is the observable diameter so much larger than 27.6 billion light-years? The answer is that space itself has been expanding while light was traveling. So the most distant regions we can see today are much farther away now than they were when their light first began its journey toward us. This is one of those ideas that seems almost designed to loosen the grip of ordinary intuition. Light has been traveling for billions of years, and during that time the universe has continued stretching. So what we see is not a static stage, but a growing one. The deepest visible cosmos is not just old. It is receding into even larger scale as space expands. And somewhere across that observable universe, stretched over its immense volume, the cosmic web extends. Not as one neat symmetrical object, not as a single centered structure, and not as a perfect lattice, but as the great pattern of filaments, nodes, walls, and voids filling the visible cosmos. The web is the architecture of matter on the largest scales we can map. So when we ask how big the cosmic web really is, the calm and honest answer is this: it is as large as the observable universe's structured matter distribution. It spans the full visible cosmos. That is already a very big answer. It means the web is not a local feature. It is not some unusually organized region near the Milky Way. It is not one special area among many different kinds of large-scale arrangements. It is the broad pattern by which matter is organized across the entire observable universe. Everywhere we look deeply enough, in every direction, the same general large-scale story appears. Matter gathers into filaments and clusters, with great voids between them. The details vary. The local patterns differ. But the overall architecture repeats. That repetition matters. It tells us that the cosmic web is not an accident of our neighborhood. It is a feature of how the universe grows. And if you let that settle for a moment, it becomes very peaceful. Every galaxy we have ever observed in the deep cosmos, every distant cluster, every faint point from the early universe that later grew into richer structure, belongs to this broader tapestry. The web is not somewhere else. It is the visible universe in its mature large-scale form. Still, saying that does not make the scale easier to feel. So it helps to slow down and build toward it. Let's begin where we always begin, at home. The Earth circles one star. That star is one among hundreds of billions in the Milky Way. The Milky Way is one galaxy in the local group. The local group sits within a larger region of gravitational influence, connected to broader structures beyond it. Those structures link through filaments into superclusters and great walls. And all of those belong to the cosmic web. What feels like a complete world from the ground is only one tiny part of one galaxy, inside one small neighborhood, inside one strand of a larger structure that extends across the observable universe. It is almost impossible to hold all those layers at once, which is why the mind benefits from taking them slowly. Each step outward changes the meaning of the previous one. The Earth is no longer simply a planet. It becomes a local point in a chain of nested structures. The Milky Way is no longer just a galaxy. It becomes one luminous inhabitant of a filamentary universe. Even the largest cosmic walls are no longer final destinations. They become strokes in the larger map of the web. And the web itself becomes something even more haunting when you realize that it does not fill the whole visible universe evenly. It gives shape to the matter within that volume. The observable universe is not packed solid with galaxies. Far from it. Much of its volume is made of voids, great underdense regions where matter is sparse. The web occupies the boundaries, the intersections, the channels, the denser pathways. So when we imagine the cosmic web spread across the observable universe, we should not picture a glowing ball filled evenly with light. We should picture a vast sponge-like or foam-like structure, where most of the drama lies in the contrast between dense threads and immense emptiness. That emptiness is part of the true size of the web too. Because the web is not defined only by what it contains, but also by the enormous spaces it surrounds. A single void can stretch hundreds of millions of light years across. A collection of such voids, stitched together by their surrounding filaments and nodes, helps shape the universe on the grandest scales. So when astronomers map the cosmic web, they are also mapping absence. The size of the web is partly the size of the nothing between its brightest concentrations. That is one of the most beautiful and strange facts in cosmology. The architecture of the universe is written in both presence and near emptiness. If you could somehow rise above the observable cosmos and look at the large-scale distribution of matter all at once, which of course no one can do, you would not see a single central knot with everything arranged around it. You would not see a neat sphere with the Milky Way in a special place. You would see a pattern of filaments, walls, nodes, and voids extending in all directions, without a preferred center, because every observer in the universe sees themselves as being at the center of their own observable horizon. The cosmic web is not centered on us. It is simply what the visible distribution of matter looks like from within an expanding universe. That idea is very important, and oddly comforting. We are not perched at a special vantage point. We are simply one small observer inside the web, looking outward. The web continues far beyond our local region in every direction we can measure. It does not begin with us or end near us. It is the common large-scale language of matter across the cosmos. There is another subtlety here that makes the size of the web even more fascinating. The cosmic web is not identical at all scales. On smaller scales, the structure is vivid and dramatic. Filaments, clusters, and voids stand out strongly. But as we zoom farther and farther out, something begins to happen. The universe starts to smooth itself. The smaller patterns blend statistically into a broader uniformity. There is thought to be a scale, often roughly around a few 100 million to perhaps around 1 billion light years depending on how one measures, beyond which the universe becomes homogeneous in the statistical sense. Not empty, not featureless locally, but smooth on average. This means the true size of the cosmic web involves a kind of paradox. On one hand, the web spans the observable universe. It is the grand pattern of structure across everything we can map. On the other hand, the most meaningful individual patterns within it do not just keep growing forever without limit. At some sufficiently large scale, the dramatic irregularities average out. The universe becomes smooth in the big picture. So the web is both universal and limited. It stretches across the visible cosmos, but its local complexity gradually dissolves into overall balance when viewed broadly enough. That is one of the gentlest ideas in cosmology. The universe allows enormous structure, but it also tends towards smoothness when seen from far enough away. Complexity lives inside simplicity. The web is real, but it is woven inside a larger statistical calm. Some astronomers call the transition into that smoothness the end of greatness, a phrase that sounds almost poetic. It does not mean the universe becomes small or uninteresting. It means there is a scale beyond which larger and larger maps stop revealing new dramatic structure in the same way. The great walls, clusters, and filaments blend into a more even cosmic average. The visible cosmos remains astonishingly large, but its texture no longer sharpens forever. And yet, within that overall smoothness, the web still fills the observable universe as the pattern of matter itself. It is like looking at the surface of an ocean from very high above. Up close there are waves, ripples, and foam. From far enough away, the ocean may appear smooth. Both views are true. The web is the wave pattern of the universe's matter distribution, extending across the full sea of the observable cosmos. If we bring the numbers back in now, they land a little differently. A 93 billion light-year observable diameter is no longer just an abstract measurement. It becomes the stage on which the cosmic web unfolds. Filaments tens or hundreds of millions of light-years long become local threads within that stage. Great walls over 1 billion light-years long become major but still partial features inside it. Voids spanning huge distances become the dark chambers between its boundaries. All of it belongs to the same immense map. And then there is the visible past. When we look deep into space, we also look back in time. The farther away a region lies, the older the light we see from it. So the cosmic web we map is not only extended across distance, it is extended across time. Nearby structure shows the universe at a relatively later age. More distant structure reveals earlier stages in cosmic history. The deepest visible reaches show matter long before it fully matured into the rich web we see closer to home. In that sense, the cosmic web across the observable universe is also a story of becoming. We are looking not only across the full visible cosmos, but across different chapters of its growth. That makes the size of the web feel even more profound. It is not just spatial scale, it is evolutionary scale. Across billions of light years, we are also tracing billions of years of cosmic history. So when someone asks how big the cosmic web really is, a fuller answer might sound like this. The cosmic web spans the observable universe, whose visible diameter is about 93 billion light-years, and within that enormous volume it organizes matter into filaments, nodes, walls, and voids. It is the large-scale pattern of the cosmos we can observe, stretching in every visible direction and carrying within it both the structure of matter and the deep history of how that structure formed. That is the scientific answer. But there is also an emotional answer. The true size of the cosmic web is the point at which the mind begins to release the idea of isolated things. On Earth, life often feels separate. One person, one place, one problem, one room, one city, one night. Even astronomy can begin that way. One star, one planet, one galaxy. But the web slowly removes that feeling of separateness. It says that galaxies belong to filaments. Filaments belong to a larger pattern. That pattern extends across the whole visible cosmos. Every bright thing is part of a greater arrangement. The true size of the web is, in a sense, the size of cosmic connectedness. Not warm connectedness. Not emotional connectedness in the human sense. But physical connectedness. Structural connectedness. A universe in which matter did not remain scattered, but organized itself over billions of years into a vast hidden architecture. This is one reason the cosmic web can feel so strangely calming before sleep. It takes the most enormous scale we can meaningfully imagine and turns it into pattern. It replaces pure chaos with structure. It replaces isolation with relation. The distances remain enormous, yes, but they are no longer only empty distance. They become part of a design. There is also something humbling, and perhaps healing, in realizing how small our own location is within that design. The Milky Way is just one galaxy among perhaps hundreds of billions within the observable universe. Our local group is a tiny neighborhood. Our planet is a dust grain in one ordinary stellar system. And yet we are able, from this small place, to infer the structure of the entire visible cosmos. That is a remarkable fact. Tiny creatures on a small planet have learned enough from light, mathematics, and patience to trace the broad architecture of the universe itself. That does not make us large, but it does make our curiosity feel beautiful. If we step back one more time, to the largest view we can meaningfully hold, the cosmic web becomes almost like a memory of gravity written across space. The early universe began with tiny density variations, incredibly subtle differences spread through primordial matter. Over time, Gravity amplified those differences. Matter gathered. Filaments formed. Clusters thickened. Voids opened. And from that patient process emerged the web, spanning the observable universe as the mature large-scale form of the cosmos. So in a very real sense, the size of the web is the size of gravity's artwork across everything we can see. And still, even with all of that, there is mystery left. The observable universe is only what we can see. Beyond it, the universe may continue much farther, perhaps forever. If so, then the cosmic web, or some continuation of large-scale structure shaped by the same laws, may extend beyond our horizon as well. We simply cannot know directly. Our view is bounded by light and time. So the true size of the cosmic web in the absolute sense may be larger than the visible portion we map. Much larger. Possibly beyond any finite picture at all. That uncertainty does not weaken the beauty of what we know. If anything, it softens it. The visible web is already more than enough to humble the imagination. We do not need infinite extension for wonder. 93 billion light-years of observable cosmic structure is already a scale so immense that the mind can only brush against it gently. Perhaps that is the best way to end this part. Not with one final number, but with a softened image. Imagine the observable universe as a vast dark sphere of visibility centered on us only because we are here to observe it. Across that sphere, matter has gathered into an intricate web of filaments, walls, nodes, and voids. Some structures stretch for hundreds of millions of light years. Some approach or exceed a billion. Between them lie regions of vast quiet emptiness. The whole visible cosmos carries this large-scale pattern, this slow architecture built by gravity over billions of years. And we, from one small galaxy inside one local part of it, have learned to see the pattern at all. That is the true size of the cosmic web, as far as our eyes and instruments can reach. It is the size of the visible universe. If this part of the journey helped your mind settle into a wider and quieter place, you can leave a gentle like, subscribe for more calm science stories, or tell me in the comments which image stays with you most. The 93 billion light-year horizon, the idea of the web spanning everything we can see, or the thought that beyond the observable edge, the pattern may continue into darkness we can never directly witness. And from here, one final question begins to glow softly in the distance. If the cosmic web spans the visible universe itself, then what created it? What invisible process, what early imprint, what long patient force turned a young and nearly uniform cosmos into this vast woven structure of galaxies and voids? That is where the story moves next. Part 8, What created the cosmic web? If the cosmic web spans the visible universe, then the next question feels almost unavoidable. What could possibly create something like that? What kind of force could shape matter into threads, knots, walls, and vast empty chambers on such a scale? And perhaps even more strangely, how could all of that structure emerge from a universe that, in its earliest visible form, seems to have been almost smooth? That is one of the most beautiful turns in the whole story. Because the cosmic web was not built by anything deliberate. No hand placed it there. No mind designed it from above. It emerged slowly, patiently, from a few simple ingredients acting across unimaginable time. Tiny differences. Invisible matter. Gravity. Expansion. And billions of years of quiet cosmic evolution. If these slow explorations help you relax into the night, you can gently support the channel with a like or a soft subscription. And if you feel like leaving a comment, I'd love to know which part of this story feels most amazing to you so far. The giant filaments, the vast voids, or the idea that all of it may have begun from almost invisible ripples in the early universe. To understand what created the cosmic web, we have to travel backward in time, long before galaxies, long before stars, long before planets, and long before anything like the Milky Way existed. We have to imagine the universe in its youth. At first glance, the early universe seems like the last place you would expect to find the origins of such a complicated structure. It was hot, dense, bright, and, in broad terms, remarkably uniform. Not perfectly uniform, but close enough that if you only heard that description, you might imagine a young cosmos with very little personality. A vast, glowing sea of matter and radiation, spread almost evenly in every direction. And yet hidden inside that near smoothness were tiny irregularities. They were not large mountains of matter, not dramatic lumps or deep gaps, just slight differences in density, tiny variations from place to place, regions that were a little denser than average, and regions that were a little thinner. At the time, those differences were incredibly small, almost absurdly small compared with the immense structure they would later produce. But in cosmology, small beginnings can matter enormously, because gravity has time. Gravity does not rush. It does not need to. Given enough time, even a slight excess of matter in one region can begin to pull more matter toward it. A place that is a little denser becomes a little more attractive, and that attraction makes it denser still. The process feeds on itself. Slowly at first, then more clearly. And over billions of years, what began as a tiny difference can become a galaxy cluster, a filament, or a giant wall. In a strange way, the cosmic web began as a whisper. A useful image is a calm lake just after a light breeze has passed over it. The surface may look mostly smooth, but there are subtle ripples everywhere. If you could freeze those ripples and then somehow let gravity act on them for billions of years, the slight highs and lows would matter. The early universe was not a lake, of course, but the principle is similar. It was smooth enough to seem simple, but not smooth enough to stay that way forever. We know those early ripples existed because the universe left behind a kind of ancient photograph. It is called the cosmic microwave background, a faint afterglow from the early universe that still surrounds us in every direction. When astronomers map it carefully, they see tiny temperature differences across the sky, extremely small variations that reflect those early density fluctuations. They are among the oldest visible clues we have to the later cosmic web. That is one of my favorite facts in cosmology. The seeds of the largest structures in the universe are still visible as faint patterns in ancient light. It means the web did not appear out of nowhere. Its beginning is still written into the oldest glow we can observe. But tiny density ripples alone are not enough to explain the full structure. To understand why the universe formed a web rather than some other pattern, we have to bring in one of the great hidden characters of modern cosmology: dark matter. If ordinary matter, the kind that makes stars, planets, oceans, bodies, and dust, were all the universe had to work with, the cosmic web would likely not have formed the way it did, or at least not nearly as quickly, and not in the same beautifully filamentary style. Dark matter changes everything. Dark matter does not shine. It does not reflect light. It does not glow in the way ordinary matter can. We do not see it directly through telescopes, but we know it is there because of its gravity. Galaxies rotate too quickly to be held together by visible matter alone. Galaxy clusters contain more gravitational pull than their luminous mass can explain. Light from distant objects bends more strongly than the visible matter in between should allow. Again and again, the universe tells us that something invisible is present, and that invisible matter outweighs the ordinary matter we know. This is one of the quiet revolutions of modern science. Most of the matter that shaped the large-scale structure of the universe is not the bright matter of stars and galaxies. It is dark matter, the unseen scaffolding beneath everything luminous. And that scaffolding mattered especially in the early universe. Ordinary matter in the young cosmos was tightly coupled to radiation. It was hot, energetic, and under pressure. It could not simply collapse wherever gravity wanted it to. It was constantly interacting with light. Dark matter was different. It did not feel that same radiation pressure. It moved mostly under gravity's influence. So while ordinary matter was still struggling in a hot bright plasma, dark matter was already beginning to gather. That gave dark matter a head start. Where the early universe had slightly denser regions, dark matter began to fall together first, building invisible concentrations. Faint gravitational wells spread across space. These growing wells became the first true framework of structure. Then, when the universe cooled enough for ordinary matter to move more freely, that matter began falling into the dark matter scaffolding that was already there. This is such a calming image if you let it settle. Before galaxies lit up the sky, the universe had already begun sketching their future positions in darkness. The web, in that sense, was invisible before it was visible. Dark matter formed the hidden pattern first, and ordinary matter later flowed into it like mist collecting in valleys. Gas gathered along the invisible filaments, cooled in denser regions, and eventually ignited into the first stars and galaxies. The bright universe we see today is, to a very large extent, the luminous tracing of a much larger dark structure beneath it. This is why cosmologists sometimes describe the cosmic web as the universe's skeleton, not because it is rigid or dead, but because it provides the underlying framework on which everything visible is arranged. So the creation of the cosmic web was not a single event. It was a long sequence. First came the tiny ripples in the early universe. Then gravity slowly amplified those ripples. Dark matter gathered into invisible structures. Ordinary matter fell into those structures. Gas concentrated along the growing filaments and in dense knots. Stars formed. Galaxies assembled. Clusters thickened. Voids expanded as matter drained away from them. And over immense stretches of time, the web became clearer and more pronounced. That last part is important. The web did not arrive fully formed. It matured. In the early universe, the differences were slight. The contrast between dense regions and empty regions was much weaker. Over billions of years, gravity sharpened that contrast. Rich regions became richer. Sparse regions became sparser. The threads thickened. The intersections brightened. The voids widened. The universe learned its structure slowly. There is something almost meditative in that idea. So much of modern life feels rushed, abrupt, immediate. But the cosmic web is the opposite. It is what happens when a few simple laws are allowed to act patiently for a very, very long time. No hurry. No sudden drama in the human sense. Just gravity doing its work in deep time. One of the most powerful confirmations of this story comes from computer simulations. When cosmologists take the known early conditions of the universe, add dark matter, ordinary matter, gravity, and cosmic expansion, and then let the simulation evolve, something extraordinary happens. The digital universe develops filaments, nodes, and voids. It begins to look like the real cosmic web. That is one of those rare moments in science where theory and observation meet with almost eerie elegance. The maps of real galaxies and the structures generated by simulation begin to resemble one another. Not perfectly in every detail, of course. Real science is never quite that tidy. But the agreement is strong enough to be deeply convincing. The same basic laws that describe gravity and cosmic evolution naturally produce a web-like universe. And once you know that, the web starts to feel less mysterious in one sense, and more mysterious in another. Less mysterious because we can trace its origins. More mysterious because it is astonishing that such immense beauty can emerge from such simple beginnings. A few physical rules. Tiny early ripples. Billions of years. And from that, a universe woven with filaments. Another gentle piece of this story involves expansion. The universe has been expanding since its earliest moments, and that expansion matters deeply. Gravity pulls matter together, but expansion stretches the overall stage on which gravity acts. The cosmic web formed not in a static box, but in a growing universe. That tension between gathering and expanding helped shape the large-scale outcome. Matter could not simply collapse into one giant central lump, because the universe itself was opening outward. So instead, structure formed in a distributed way, with localized gathering occurring across an expanding cosmic landscape. This balance helped the web become a web. Too much collapse in too little expansion, and the picture would be very different. Too much smooth expansion without enough gravitational gathering, and rich structure might never have emerged at all. The universe, as far as we can tell, evolved in a way that allowed both. Expansion made room. Gravity created pattern. That balance still feels almost miraculous, even when described scientifically. And then there are the voids. It can be tempting to think only about the dense parts when talking about the creation of the web. The filaments, the clusters, the glowing intersections. But the voids were created at the same time, as part of the same process. As matter flowed towards slightly denser regions, other regions were left behind. They became more empty by comparison. Over time, those underdense regions expanded and cleared out further, not into perfect nothingness, but into great cosmic deserts with far less matter than average. So the voids are not empty accidents. They are the natural counterpart to the rich structures around them. The universe did not merely build filaments. It also carved absence. That is one of the most poetic truths in the whole subject. The web was created not only by accumulation, but by evacuation. Not only by what gravity gathered, but by what it left behind. If you could watch the web forming across billions of years in fast motion, you would see matter flowing away from some regions and toward others, like an impossibly slow tide. Dense knots would grow brighter. Thin bridges would stretch between them. Wide empty basins would open around them. It would not look like construction in the human sense. It would look more like emergence. That word feels right here. Emergence. The web emerged from conditions that did not explicitly contain visible filaments, just as a snowflake emerges from water molecules without anyone drawing its pattern first, or a coastline emerges from geology and erosion without a planner laying out its curves. Nature has ways of generating form from law. The cosmic web is one of the greatest examples. It is also worth remembering that the first galaxies formed inside this evolving framework. They were not random fires lit in empty darkness. They ignited where gas gathered deeply enough inside dark matter halos. So in a very literal sense, the web guided where galaxies could most easily appear. The universe's first great luminous structures were born in places that gravity had already prepared. That changes the emotional meaning of galaxies a little. A galaxy is not just an isolated achievement of matter. It is also a local consequence of a much larger architecture. And our own galaxy belongs to that story too. The Milky Way did not appear in a random patch of space. It formed inside the broader cosmic framework shaped by dark matter and large-scale structure. Our local corner of the universe was part of the web long before the sun existed, long before Earth existed, long before life learned to look up and wonder. That thought always feels surprisingly intimate to me. The atoms in your body were forged in stars inside a galaxy that itself formed along pathways laid down by the deep structure of the cosmos. We tend to think of our lives as local, and of course they are. But locally, we live inside a galaxy. That galaxy lives inside the web. And the web began forming from the earliest ripples in the universe. There is no sharp line where our story stops being part of that larger one. Now, there is still much we do not know. We do not yet fully understand the true nature of dark matter. We do not fully understand every detail of how the earliest fluctuations were generated. There are open questions about the fine structure of filaments, the role of feedback from galaxies and black holes, and how different environments in the web influence later cosmic evolution. Science has explained a great deal, but not everything. And somehow that incompleteness feels right. A subject this large should still have mystery in it. What matters for our story tonight is the broad, beautiful outline. The cosmic web was created because the early universe was not perfectly smooth. Tiny ripples gave gravity something to work with. Dark matter gathered first and built the invisible framework. Ordinary matter followed, flowing into the hidden scaffolding. Gas cooled. Stars formed. Galaxies assembled. Dense regions thickened. Empty regions cleared. Over billions of years, the universe transformed from a nearly uniform young cosmos into the woven large-scale structure we see today. That is the creation story of the web, not a single dramatic act, but a long patient becoming. And perhaps that is why this part of cosmology feels so deeply restful. It reminds us that complexity can grow from simplicity, that enormous structures can emerge from small beginnings, that quiet forces, given enough time, can shape worlds, galaxies, and the entire visible architecture of the universe. There is a softness in that thought. You do not need to imagine the universe as loud or chaotic to understand its power. Much of its greatest work has been done slowly. A slight excess of matter here, a little more gravity there, a gradual deepening of structure over billions of years. The web is not a cosmic explosion frozen in place. It is the memory of countless small imbalances patiently amplified. If this part of the journey has helped your mind settle into a calmer rhythm, you can leave a gentle like, subscribe for more quiet explorations of science, or share in the comments which image stays with you most. The tiny ripples in the early universe, the invisible dark matter skeleton, or ordinary matter slowly falling into place and lighting up the web. And from here, one final, more intimate question begins to come into focus. If the cosmic web was created by dark matter and gravity, and if galaxies formed inside that vast hidden framework, then what is our own place inside it? Where does the Milky Way sit in the web? Which filament, which neighborhood, which great structure contains the galaxy we call home? That is where the story comes home again. Part 9, The Invisible Skeleton of the Universe. By now, the cosmic web may already feel large enough to be unreal. Filaments stretching across millions of light years. Great walls spanning distances that challenge the mind. Voids so vast that even emptiness begins to feel like a structure of its own. And yet beneath all of that, under the galaxies and the glowing gas and the patterns we can map with telescopes, there is something even stranger waiting quietly in the dark. Most of the web is invisible. Not hidden in the ordinary sense, like something dim waiting for a better camera. Not invisible because it is too far away or too small. Invisible because it does not shine at all. It does not reflect light. It does not glow softly in the dark. And still, without it, the universe as we know it would not have taken the shape it did. The great web of matter, the very structure we have been following across the observable cosmos, seems to rest on a deeper framework we cannot see directly. This is why cosmologists sometimes call the cosmic web the invisible skeleton of the universe. It is a gentle phrase, but a powerful one. A skeleton is not the whole body. It does not show you color or warmth or motion or light, but it gives everything form. It supports, guides, and holds the larger shape together. And in much the same way, dark matter appears to provide the hidden framework beneath the visible universe, the underlying arrangement around which galaxies gathered and within which they still live. If these quiet journeys through science help you slow down at night, you can gently support the channel with a like or a soft subscription. And if you feel like it, leave a comment with the part of the cosmic web that feels most haunting to you. The glowing filaments, the giant voids, or the idea that almost everything shaping the universe's structure cannot be seen at all. There is something deeply human about wanting to trust what we can see. We grow up believing vision gives us reality. If something is there, we imagine it should appear. But modern cosmology keeps asking us to become more patient than that. Again and again, it tells us that reality is not limited to what shines. Dark matter is one of the clearest examples. We cannot point to it in a photograph the way we point to a star or a galaxy. But we see its influence everywhere. We see galaxies rotating faster than visible matter alone should allow. We see clusters of galaxies exerting more gravity than their luminous contents can explain. We see the light from distant objects bending around invisible mass, as though a hidden hand is quietly shaping the path of what we observe. And on the largest scales, we see something else. We see galaxies arranged in a web-like structure that theoretical models reproduce best when dark matter is included as the dominant framework beneath ordinary matter. So in a strange way, the invisible skeleton of the universe is known not through sight, but through consequence. We do not see the skeleton itself. We see the body it shaped. That idea is worth lingering with, because it changes how the web feels in the mind. The bright galaxies mapped in surveys are not the whole story. They are more like dewdrops clinging to an unseen structure. They reveal the pattern, but they do not create it on their own. The filaments we trace in galaxy maps are, in a deeper sense, luminous traces of a much larger dark matter network beneath them. This means the visible universe is almost like a sketch drawn over an invisible blueprint. And perhaps that is one of the most beautiful ways to imagine it. If you could somehow strip away all the stars, all the glowing gas, all the bright galaxies that make the night sky feel alive, the deeper large-scale form of the universe would still remain. The dark matter would still be there, stretched into halos and filaments, arranged into the hidden framework that gravity built from the earliest density fluctuations of the young cosmos. The universe would look much dimmer, of course, almost impossible to picture in ordinary terms. But its structure would still exist. The light came later. The skeleton came first. In Part 8, we talked about how the early universe contained tiny ripples in density, and how dark matter, freed from the pressure that affected ordinary matter, began gathering around those ripples early on. That early gathering produced the first invisible wells and pathways of structure. Now, in this part, we are standing deeper inside the consequences of that process. We are looking at what it means that the visible universe formed inside an invisible one. A useful way to picture this is to imagine frost forming on a cold window. The frost traces underlying patterns of temperature, moisture, and surface texture that you cannot see directly. What becomes visible is not the entire reality, but the visible expression of deeper conditions beneath it. Galaxies are something like that. They are the glowing outcome of a hidden large-scale structure shaped by dark matter and gravity. Another image that helps is thinking of valleys in a landscape. Rainwater does not choose its path at random. It follows gravity into channels already implied by the shape of the land. In the same way, ordinary matter in the universe did not gather everywhere equally. It flowed toward the invisible gravitational valleys created by dark matter. Gas fell inward, collected in halos, streamed along filaments, and eventually reached the densities needed to form stars and galaxies. The visible universe followed the shape of something unseen. That is why the phrase invisible skeleton is so fitting. The skeleton does not merely support visible matter. It guides where visible matter can most naturally go. And if you let that settle, it gives the cosmic web a kind of quiet inevitability. The galaxies were not simply scattered first and connected later by our imagination. They formed inside a real gravitational framework. The web was not a pattern painted on afterward. It was part of the universe's deep structure from very early on. This also explains why galaxies are not distributed evenly. Their positions reflect the long history of matter falling into dark matter structures. A galaxy cluster marks a place where dark matter and ordinary matter both gathered strongly. A filament marks a channel where dark matter formed an extended bridge and ordinary matter followed. A void marks a place where there was less material to begin with and from which matter gradually drained away as surrounding structures grew. Once you see the cosmic web this way, the visible universe starts to look less like a collection of separate objects and more like the illuminated skin of a deeper hidden anatomy. That anatomy matters for another reason too. It does not only explain where galaxies formed, it also affects how they evolve afterward. Galaxies are shaped by environment. A galaxy deep inside a dense cluster experiences a different cosmic life from one drifting in relative isolation near a void. Inside dense regions, galaxies are more likely to interact, merge, lose gas, or be influenced by the hot intracluster medium around them. Along filaments, galaxies may receive fresh gas, move along preferred directions, or gradually fall toward larger nodes. In quieter regions, galaxies may evolve more gently, with fewer close encounters and a calmer supply of matter. So the skeleton is not just a static stage, it is also a kind of ongoing environment. It influences the pace and style of galactic life. That is a subtle but important form of connectedness. The Milky Way is not just a galaxy floating freely in abstract space. It exists in a particular cosmic neighborhood, inside a particular large-scale arrangement of matter, shaped by the local conditions of the web around it. Our own history, in that sense, is not detached from the cosmic skeleton. It unfolded within it. There is something calming about this. It turns the universe into something more textured and less lonely. Galaxies are not simply isolated lights. They belong to places. They inherit context. They grow differently depending on where they are embedded in the larger structure. And the same is true of the web itself. Its filaments are not decorative strands. They are channels through which matter moves. They connect the dense intersections of the universe. They feed galaxy clusters. They help define how the overall cosmic landscape develops over time. Much of this hidden skeleton has been revealed not by direct sight, but through techniques that are almost poetic in their indirectness. One of the most powerful is gravitational lensing. According to general relativity, mass bends spacetime, and light follows that bending. So when the light from a distant galaxy passes through a region filled with mass, whether that mass is visible or dark, the light's path is subtly distorted. By measuring those distortions across many background galaxies, astronomers can begin to map where invisible mass must be located. This is one of the gentlest miracles in science. Dark matter cannot be seen directly, and yet it can be traced through the way it bends the light of more distant objects. The invisible leaves fingerprints in geometry itself. It changes the shape of what lies behind it, and from those changes, patient observers can reconstruct the hidden structure in front. There are places in the universe where lensing maps have shown dark matter concentrated around galaxy clusters in ways that align beautifully with the idea of a larger invisible framework. In some cases, researchers have even begun inferring the dark bridges that seem to stretch between clusters, the faint connective tissue linking brighter nodes together. These detections are challenging and often delicate, but they matter deeply, because they help move the cosmic web from theory and simulation into more direct observational reality. Another way the invisible skeleton reveals itself is through the hot gas lying between galaxies. As we mentioned earlier, filaments are not only made of galaxies and dark matter. They also contain diffuse gas, often extremely hot and very thinly spread. Detecting this gas can be difficult, but when astronomers do find it, especially in the regions where simulations predict filaments should lie, it provides another clue that the invisible framework is real and physically populated. The picture that emerges is deeply consistent. Dark matter forms the backbone. Gas follows. Galaxies light up along the densest regions. Clusters grow where multiple pathways meet. Voids open where matter is sparse. The visible web and the invisible skeleton are not two different things. They are two layers of the same cosmic structure. There is something strangely restful in that layered reality. It suggests that the universe is not shallow. It has hidden depth even in its large-scale form. What we see is meaningful, but not complete. There is always more beneath the visible surface. And somehow that makes the universe feel richer, not colder. Maybe this is because human life also unfolds through unseen structures. We live inside social networks, inherited histories, unspoken patterns, invisible forces of culture and memory that shape what becomes visible in the present. The cosmic web is not the same as those things, of course, but it carries the same philosophical softness. The visible surface of reality is often not the whole explanation. Form comes from hidden order. Now, there is still much we do not know about dark matter itself. We know what it does far better than we know what it is. That remains one of the great open questions in physics. Is dark matter made of some new particle not yet detected in laboratories? Is it something more exotic? Could there be aspects of gravity we do not yet fully understand? These questions are still alive, and they matter enormously. But even without knowing its ultimate nature, we can still appreciate its large-scale role. Whatever dark matter turns out to be in detail, the evidence strongly suggests it helped shape the cosmic web and continues to define the hidden skeleton beneath the luminous universe. And that brings us to one of the most haunting implications of all. The things we find most beautiful in space, galaxies glowing across deep time, maybe only the visible flowers growing from roots we cannot see. That thought changes the emotional meaning of the night sky. The stars remain beautiful, yes. The galaxies remain staggering. But behind them lies a deeper beauty, a structural one. The beauty of an invisible framework patiently organizing matter over billions of years. Even the great voids begin to feel different through this lens. A void is not just an absence of visible galaxies. It is part of the broader arrangement of the skeleton itself. A place where less matter accumulated, where the hidden framework did not thicken as strongly, and from which matter moved away as surrounding structures grew. The web is not only its bright strands. It is also the spaces the skeleton leaves behind. And perhaps that is why the cosmic web feels so complete as an image. It includes both the seen and the unseen, the light and the dark, the dense and the empty, the visible branches and the invisible trunk. If you could somehow watch the universe from the outside, which again no one can, you might see the visible galaxies gradually tracing the hidden dark matter scaffold, lighting up its densest pathways like frost on a branch or sparks along a wire. The skeleton would remain mostly dark, but its form would become legible through the matter settling into it. Over time, more of the structure would reveal itself through consequence. Not because the dark matter became luminous, but because the ordinary matter growing within it gave it shape. In some sense, this is what cosmology itself has done. Humanity has learned to read the visible universe as a guide to the invisible one. The galaxies are not just destinations. They are clues. That is a very tender kind of science. It is not based on conquest. It is based on inference, on noticing patterns carefully enough to understand what must lie beneath them. And when you apply that to the entire observable universe, the result is breathtaking. The universe is not merely decorated with galaxies. It is built around a hidden structure more massive and more extensive than the luminous world we usually imagine. What we call the cosmic web is partly our name for that realization. That beneath the shining surface of the cosmos lies an invisible skeleton giving it form. By now, perhaps the phrase no longer feels abstract. It feels physical, real. A skeleton of dark matter halos and filaments. A framework laid down early in cosmic history. A hidden structure that ordinary matter entered, illuminated, and continues to inhabit. A universe whose visible beauty depends on something mostly unseen. There is one more quiet truth in all this. The invisible skeleton is not separate from us. We are not observers outside it, safely looking in. We are inside it. Our galaxy formed within this larger framework. Our local group of galaxies is embedded within it. The Milky Way's motion, environment, and long-term future are all part of this larger geography. Even the calm patch of sky above your house tonight belongs to a galaxy nested inside a much bigger structure than the eye can reveal. And that makes the final step in the story feel very natural. Once you understand the hidden skeleton, you begin to want orientation. If the universe has this vast invisible framework, then where are we inside it? Which part of the web contains the Milky Way? Are we near a dense node, deep in a filament, close to a void, or living in some quieter edge of the cosmic landscape? That question brings the story home again. If this part of the journey has helped your mind drift into a quieter place, you can leave a gentle like, subscribe for more slow explorations of science, or tell me in the comments which image stays with you most tonight. Galaxies as dewdrops on an unseen web, dark matter bending light through gravitational lensing, or the idea that the entire visible universe is built on an invisible skeleton. And as we move into the final part, the scale becomes more personal in the most cosmic way possible. Because after all the giant structures, the early ripples, the hidden dark matter scaffold, and the web spanning the observable universe, one simple question remains. Where, inside all of this, are we? Where does the Milky Way sit in the cosmic web? And what does our own quiet address in the universe really look like? One small note before we continue later. Some of your earlier uploaded reference files have expired on my side, so I'm continuing from the tone we've already established together here. If you want me to recheck those original files directly again, just upload them once more. Part 10, Where Our Galaxy Sits in the Cosmic Web. After all the great walls, invisible filaments, ancient ripples, and vast dark voids, it is comforting to come home again. Because once you have followed the cosmic web all the way out to the largest patterns in the observable universe, one soft question remains. Not how big the web is, not what created it, not even what hidden matter holds it together, but something simpler, and somehow more intimate. Where are we inside it? Where, exactly, does the Milky Way sit in this immense woven structure of matter and emptiness? It is one thing to talk about the universe in the abstract, to drift through ideas that stretch across billions of light years. It is another thing entirely to ask for our address, to ask where our own galaxy belongs in the quiet architecture of the cosmos. And the answer is surprisingly gentle. We do not live in one of the most violent crossroads of the universe. We do not appear to sit in one of its grandest dense intersections. We live in a quieter neighborhood, on a smaller branch of a much larger design. And maybe that is a comforting place to end. If these calm journeys through science help you slow down at night, you can gently support the channel with a like or a soft subscription. And if you feel like it, you can leave a comment sharing where you're listening from, or which part of the cosmic web stays with you most. Sometimes it is the giant voids. Sometimes the invisible dark matter. And sometimes it is simply the thought that our galaxy has a place inside something so much larger than itself. To find our place in the web, we have to start with the smallest familiar layer and slowly move outward again. The Earth circles the Sun. The Sun is one ordinary star among hundreds of billions in the Milky Way. The Milky Way is a large spiral galaxy, a broad rotating city of stars, gas, dust, and dark matter stretching about 100,000 light-years across. It contains spiral arms, nebulae, star clusters, black holes, and all the hidden machinery of galactic life. From inside it, the Milky Way feels almost complete, as though it could be a universe all by itself. But it is not alone. The Milky Way belongs to a small gathering of galaxies called the Local Group. This is our first real step beyond ourselves in the cosmic web, the first widening of the map that begins to place our home in context. The Local Group is not a huge cluster packed with thousands of galaxies. It is more modest than that, more like a quiet neighborhood than a great metropolitan center. It contains more than 50 known galaxies, though most of them are small dwarf galaxies. The two largest members are the Milky Way and Andromeda, with the Triangulum Galaxy as another notable member, along with many smaller companions circling the larger systems. Already, this tells us something about where we live. We are not in total isolation, but we are not in one of the universe's grandest cities either. Our galaxy belongs to a family, but a relatively small one. And that family is not static. The Milky Way and Andromeda are moving toward each other. Over unimaginably long timescales, they are expected to merge, creating a new, larger galaxy from the slow gravitational dance of both systems. Even here, in our quiet local neighborhood, the cosmic web is not a frozen backdrop. It is an evolving place. Galaxies gather. They interact. They fall inward. The great architecture of the universe remains active even on the scale closest to home. If we step outward from the local group, the picture becomes a little more subtle. For a long time, people often imagined galaxy groups and clusters as islands floating separately in a sea of space. But in the language of the cosmic web, even our local group is part of a larger environment. It does not sit randomly. It lies within a broader filamentary region of the universe, one of the quieter pathways of the web. Some astronomers describe our immediate larger-scale surroundings in terms of local sheets and neighboring voids, a landscape in which galaxies are not evenly scattered, but arranged in a kind of gently flattened structure with emptier regions nearby. That may sound a little technical at first, but the emotional meaning is simple. Our galaxy lives on a smaller branch of the web, not at one of the brightest and busiest knots. In other words, we are in the suburbs. Cosmically speaking, that is not a bad place to be. There is something soothing about this image. If the universe were a giant woven structure full of dense intersections and long roads of matter, then the Milky Way seems to sit along a quieter route rather than in a central traffic hub. We are not in a region packed with thousands of giant galaxies all crowding one another at close quarters. We occupy a calmer environment, one with room, one with distance, one where the night sky from within our galaxy can still feel dark and spacious. And beyond the local group lies one of the next great landmarks in our region of the universe, the Virgo cluster. The Virgo cluster is a much larger collection of galaxies than our local group. It contains hundreds, even thousands, of galaxies depending on how one defines its boundaries and members. It is one of the dominant mass concentrations in our wider cosmic neighborhood, and for a long time astronomers spoke of our galaxy as belonging to a broader structure called the Virgo supercluster, named after that great nearby concentration of galaxies. That older picture still carries some useful truth. The Virgo cluster really is one of the major dense regions in our part of the universe. Its gravity matters. Its presence helps define the surrounding cosmic geography. Our local group is not inside the Virgo cluster itself, but it lies in the same broader regional system. The Milky Way is influenced by a larger gravitational landscape in which Virgo plays an important role. More recently, astronomers introduced an even wider concept called the Laniakea supercluster. The name means something like immense heaven, and it is one of those rare scientific names that feels as poetic as the thing it describes. Laniakea is not a simple compact cluster. It is a vast region defined partly by how galaxies move under gravity, how they flow through space toward denser centers. In that picture, the local group, the Virgo cluster, and many other neighboring galaxy groups all belong to this broader gravitational basin. There is something especially calming about that idea. It suggests that our galaxy is not merely placed in the web like a dot on a static diagram. It is part of a large-scale flow, a larger pattern of motion. Galaxies in our region drift within the hidden contours of gravity, much as raindrops on a broad landscape eventually find their way toward deeper valleys. The cosmic web is not only structure. It is movement through structure. And still, even inside Laniakea, we are not in the center of everything. We are not in a special throne room of the cosmos. We are in one small group, in one modest part of a much larger gravitational territory. That humility is part of the beauty. If we try to picture our place visually, it helps to imagine the cosmic web not as a rigid diagram, but as a broad terrain of density. There are very dense nodes where major clusters gather. There are long filaments connecting them. There are quieter side paths. And there are enormous voids nearby where matter is much thinner. The Milky Way seems to live in one of the less crowded parts of this terrain, not in a deep void, but not at a major node either. We are connected, but quietly connected. We are part of the web, but from a comparatively calm address. That is a wonderful sentence to rest with for a moment. We are part of the web, but from a comparatively calm address. And that may be one reason the sky above us looks the way it does. We do not live inside the glare of a giant galaxy cluster. We are not surrounded in every direction by dense crowds of massive galaxies. From Earth, the night can still be dark. The stars can still appear isolated and serene. Our local region of the web allows a kind of quiet. We live in a place where structure exists, but distance still dominates the feeling of space. There is another subtle beauty in this. The Milky Way is not only located in the web, it is also one of the luminous expressions of the web. Our galaxy formed where matter gathered in a dark matter halo that itself belonged to the larger cosmic skeleton. The stars of the Milky Way, the gas in its spiral arms, the planets orbiting within it, and even the atoms in your body all ultimately trace their existence back to our galaxy's place inside that hidden framework. This means our home is not separate from the cosmic web story. It is one consequence of it. Sometimes astronomy can feel as though it is always moving farther away from us, as though every answer takes us deeper into remoteness. But here the story bends back inward. The cosmic web is not just something far away that scientists map on computers. It shaped the conditions under which our galaxy formed. It helped determine where matter gathered, where stars ignited, where galaxies became possible. So when we ask where the Milky Way sits in the web, we are also asking where the long prehistory of our own existence was set into place. That is a very tender idea. Our local address in the universe is part of the reason there was ever a local story at all. And if we zoom inward for a moment, even the Milky Way has its own quiet internal geography. The Sun does not sit at the center of the galaxy. It lies in one of the spiral arms, or more precisely in a smaller structure often called the Orion Arm or Orion Spur, a minor branch between larger spiral arms. Even within our own galaxy, we are not at the center. We are off to one side, circling quietly through a luminous river of stars. That nested modesty is beautiful. Earth is not at the center of the solar system. The Sun is not at the center of the galaxy. The Milky Way is not at the center of the local group. The local group is not the center of Laniakea. And Laniakea is not the center of the universe. At every scale, we find that our place is real, meaningful, and specific, but not central. And maybe that is one of the deepest lessons the cosmic web offers. Meaning does not require centrality. We do not need to occupy a privileged position for our perspective to matter. A small world in a quiet branch of the cosmic web can still look outward and discover the shape of the whole. There is another aspect of our location that makes it especially haunting. Some studies suggest that our galaxy lies near or within a relatively underdense region, part of the quieter outskirts of large-scale structure rather than one of its crowded metropolitan centers. That does not mean we float in total emptiness. Clearly we do not. We live among galaxies, groups, and larger structures. But it does mean our neighborhood may be a little quieter than average, a little less crowded, a little farther from the densest concentrations of matter. If true in the broader sense, that makes our place in the universe feel almost rural. Not lonely, exactly, but spacious. There is something deeply soothing about cosmic spaciousness. It means the darkness between things is not merely absence. It is part of the architecture. The open regions, the long distances, the calmer neighborhoods, all belong to the same great design. And our galaxy seems to inhabit one of those calmer regions, one of those places where the universe leaves more room between its brightest gatherings. Of course, from inside the Milky Way, the sky does not announce any of this directly. On a clear night, you do not look up and immediately see filaments or nodes or gravitational basins. You see stars. You may see the pale band of the Milky Way if the sky is dark enough. You may sense depth, but not structure on the largest scales. Our place in the web had to be discovered indirectly, through galaxy maps, redshift surveys, gravitational theory, and patient cosmic cartography. That makes our address even more special in a quiet way. We did not inherit it as obvious knowledge. We uncovered it. Humanity learned, step by step, how to place itself in the larger map. First Earth, then the solar system, then the galaxy, then the local group, then the supercluster, then the cosmic web. Each widening did not erase the smaller home beneath it. It placed it inside something larger. And perhaps that is what makes cosmology feel both humbling and strangely peaceful. It is a series of enlargements that leave us smaller, but also more connected. The Milky Way belongs to the web. That sentence is simple, but it carries a great deal of weight. It means our galaxy is not an isolated island floating in an otherwise meaningless emptiness. It means we are part of a physical relationship extending across millions and billions of light years. Our local galaxy group is connected to broader structures. Those structures link to others. Matter flows through these connections. Gravity shapes them over immense time. The visible universe, at its deepest level, is less a scatter of separate lights than a woven terrain of neighborhoods, roots, intersections, and voids. And we are somewhere inside that terrain, quietly riding along with our local branch. There is one final thought here that feels especially fitting for the end of a sleep story about cosmic scale. When you ask where the Milky Way sits in the cosmic web, you are really asking two questions at once. One is scientific. Which group, cluster, supercluster, or filament contains us? The other is emotional. What kind of place do we live in, cosmically speaking? And the emotional answer seems to be this. We live in a calm region of a vast and structured universe. Not at the center. Not at the edge of all things. Not in one of the most violent giant intersections. But in a quieter branch, in a galaxy rich enough for stars and planets and life, in a local group small enough to leave room for darkness, in a web large enough to connect us to the whole visible cosmos. That is a beautiful address. It means that when you look up at the night sky, even though the stars appear scattered and the darkness feels empty, you are really looking out from within one woven thread of a much larger pattern. Somewhere beyond what the eye can see, beyond the Milky Way's glow, beyond Andromeda, beyond the Virgo cluster, beyond the great walls and the vast voids, the cosmic web continues, extending across the observable universe. And our galaxy, with all its quiet beauty, is part of that design. The sun, the earth, your room, this moment of listening, all of it exists inside one galaxy, inside one small galactic group, inside one branch of the cosmic web. There is something profoundly restful in that, not because it makes us important in the grandest sense, but because it gives us place. And perhaps that is the final gift of the cosmic web. After all the scale, all the mystery, all the invisible matter and the huge distances, it gives us orientation. It tells us that the universe is not only vast, it is structured. It has pathways and neighborhoods. It has crowded regions and quiet ones. It has homes, if we are willing to use that word carefully. And our home is one small, calm address in an immense woven cosmos. If this long journey through the cosmic web helped you unwind tonight, you can leave a gentle like, subscribe for more slow science stories, or share in the comments which idea stayed with you most all the way to the end. Was it the giant voids, the invisible dark matter skeleton, the scale of the web across the observable universe, or simply the thought that the Milky Way itself is only one quiet thread in something far larger? And now, as the mind begins to slow, let the whole picture soften. A young universe, almost smooth, holding tiny ripples. Dark matter gathering first in silence. Gravity pulling patiently over billions of years. Filaments forming. Voids opening. Galaxies lighting up the hidden skeleton. Great structures rising across the observable cosmos. And somewhere, in a modest spiral galaxy on a quiet branch of that web, a small world learning to look outward. That is where we are. Not nowhere. Not everywhere. But somewhere real, somewhere calm, somewhere woven into the larger design. A small address in a very large universe. And maybe that is enough. One small note before we keep going later. I matched this to the tone we built together in chat. If you want me to directly recheck the original uploaded reference files again for the next step, just re-upload them, because some of the earlier uploads have expired on my side.